to cover another fascinating concept, which is the paradigm of single instruction, multiple data processing that has influenced computer architectures quite a bit. Essentially, all computer architectures have this today. That was not true in the past, but it was so important that every computer architecture has built single instruction, multiple data support, either as part of a separate processor like a GPU, or as part of a separate functional unit, like a SIMD functional unit today. But before we get to that, this is where we are. Essentially, we're covering execution paradigms, and we have SIMD architectures and graphics processing units, which build on SIMD architectures left today and next week, essentially. We've covered everything else except for decoupled access and execute, which I'm going to refer you to this optional lecture. It's only 11 or 12 minutes. This is another paradigm that's actually used in existing systems. The idea of decoupling access, memory access and execute so that they can run asynchronously to each other so that you can overlap the latencies of memory and execution units in different ways, essentially. That's the idea, basically. But this short lecture goes into a little bit more detail, if you will. Now, before we start SIMD, let's wrap up systolic arrays. We've covered systolic arrays and VLIW yesterday. And we were discussing essentially systolic arrays are specialized architectures to accelerate specialized computations. And this was the computation we looked at yesterday. And we also said these have influenced real systems. I want to talk a little bit more about the real systems because we kind of rushed through it yesterday. But essentially, this TPU that was developed by Google starting in 2014-15, and it was described in the SYSCA 2017 paper, is essentially a systolic array. Basically, you can even read that they say systolic data flow of the matrix multiply unit. Software has the illusion that each 256-byte input is read at once, and they instantly update one location of each 256 accumulator RAMs. Basically, they accumulate, do multiply and accumulate to do matrix multiplication, essentially. Again, I won't go into the details, but you can see how they do it. It's transparent to the software, so they basically translate a multiply and accumulate operation, a large one, a matrix multiplication essentially, to the systolic computation using a lot of support in the system. So this is the systolic computation unit. And this is actually somewhat similar to what we have discussed. Exact data flow and exactly what is accumulated inside each unit is different, of course, because you can actually design systolic arrays for matrix multiplication in many, many different ways. But you can see that this is the support that they provide. According to them, this is the matrix multiply unit. And you can see that there's a lot of support to input the data into this unit and also input the weights that they're multiplying things with, because this is really doing matrix multiplication for convolutions, for example, like we discussed yesterday. So you need to actually feed the weights and feed the data vectors from here and then get the data out from here. Okay, I won't go into the details. You can read the paper if you're interested, but it's doing essentially matrix multiplication. Yes. Not necessarily, yeah, not necessarily. So they're probably taking advantage of the reordering internally. As long as you get the right result, it doesn't matter which order you follow. But yeah, if you think about that, in a von Neumann architecture, you have a sequential order dictated by the program, right? You have to obey that order because that's the architecture you have. Here, a lot of things can be happening concurrently. So that's one of the other benefits of systolic architectures. You're not tied to an order. Okay, so they later, so the reason they built this was to actually accelerate inference first as well, and then training next in the Google data centers, because they're doing a lot of data analytics clearly internally. And later they basically said, we have so much infrastructure that we can actually amortize the cost of building our own chips. And that's why they actually did this. So they actually amortize the cost of building their own chips, total cost of ownership, as opposed to getting GPUs from someone else, for example. And they kept building this. This is TPU 2. They actually do training on this one, as opposed to just inference in neural networks. And they basically increase the memory bandwidth, as you can see. So providing data into the systolic array is still important, even though the systolic array is more efficient than a general purpose processor, like a CPU, in terms of how much benefit, how much computation it does on a given data element that it fetches from memory, like we discussed yesterday. It still needs a lot of data because these are quite data intensive applications. So they basically replace the traditional memories with high bandwidth memories. As you can see, they actually add floating point operations and they increase the computational power. And then TPU3 has even higher bandwidth and larger memories, more matrix units, as you can see, not just 2 systolic arrays, but 4 systolic arrays now. And then the teraflops is increasing. And this is the latest one that they have exposed at least. And they're targeting many, many applications over here. You can see that the total teraflops per chip has increased, increased by almost 3 times, as you can see over here. So they've been improving this over time, and you can read more papers about it. So they've been quite public about it. Even though they don't disclose exact details, they talk about some of the things that they've done. Okay, but I will also mention that we've been analyzing these TPUs in my research group together with Google, as you can see in this work. And we've been finding that a lot of the issues that they have is really due to memory. And we're going to talk about memory after next lecture, hopefully. We're going to go into the memory design. And this is to motivate the importance of memory, basically. You can see that all of these chips are increasing their memory bandwidth, making memory more expensive, increasing their memory capacity, yet they still need more memory. So in large machine learning models, especially, for example, long short-term memories, transformers, etc., basically more than 90% of the entire system energy is spent on memory. Okay, we'll get back to that. So now this is systolic arrays. As I mentioned yesterday, systolic arrays are not the only machine learning accelerators. Now we're going to see the SIMD paradigm that people have been using to accelerate machine learning, because SIMD is actually a very good fit for doing convolution type parallel operations, matrix multiplication. And yesterday we saw that how you can convert convolution to matrix multiplication as well, right? Remember that slide where I showed you that? You can go back to that. So basically, people have been using SIMD architectures, and this is later today. I will show you that at the core of it, this has many processors inside. Well, this is the newer version, if you will. This has many processors inside, and each processor is a SIMD processor internally, and they communicate with each other. So it actually consists of multiple paradigms. It's a multiprocessor of SIMD processors or vector processors, if you will. And this is designed as a wafer scale chip, and there are lots of units over here, according to Cerebrus, 850,000 cores. And this has large amounts of on-chip memory, 40 gigabytes of memory, SRAM on top of the chip. So they're putting large amounts of computation memory together. But this is a different approach, clearly, compared to systolic arrays. And you can learn more about this in this talk that was delivered by the CEO or CTO of that company. Okay, I should also say that people have been using FPGAs for this. Microsoft has developed this brainwave system that they call. Essentially, they use FPGAs as a substrate to accelerate machine learning operations. And they do multiple things. Partly, they do some specialized data flow mapping, as you can probably see somewhere over here. I mean, you need to read the paper, but the paper doesn't give a lot of detail. But they do partly data flow mapping, directly accelerate part of the data computation. But they also put soft SIMD units on the FPGA, just like you're doing in your labs right now. You're putting a soft processor, MIPS processor on the FPGA, right? You're not mapping, accelerating an application. You're basically implementing a processor on the FPGA substrate. They actually have a SIMD processor on the FPGA substrate also. At the end of this lecture, we may get back to it, even though we're not going to go into much detail because they don't go into much detail anyway. Okay, but you can see that now there are multiple ways of accelerating things, and clearly SIMD plays a large role. And the reason is SIMD is very good at exploiting a particular type of parallelism, which is called data parallelism, if you will. Essentially, you're doing many of the same operations on different data elements. And GPUs exploit the same type of parallelism. I call this regular parallelism also. Of course, there are many types of regular parallelism. In this particular case, you're doing the same operations on many pieces of data elements. So we're going to talk about that. But before we talk about that, let's talk about the taxonomy of computers. We've been actually covering different types of computers. And this paper, that's a seminal paper by Mike Flynn, you can see that almost 60 years ago, categorizes computers into 4 different categories in terms of how many instructions do what to how many pieces of data elements. So you have instructions on the x-axis and the data elements on the y-axis. And the simplest machine is doing a single instruction operates on a single data element. This is a scalar machine, like we have seen, right? The ISA is doing this. Essentially, you do an add. Essentially, each operand has a single data element. Right? This is the traditional add we have seen. And we've accelerated this using out-of-order execution, for example. And then there's SIMD, which we're going to see. In this case, a single operation. Each operand is not a single element, but it's really a vector of elements. So it's many elements at the same time. So you're operating on vectors, essentially. And there are two types of these, array processor and vector processors. And this is a distinction of a purist, and we're going to see the distinction. Array processor essentially does the same operation to different elements in the same time across different elements. Vector processor does the same operation on different elements across time, essentially. MISD is interesting. This is kind of similar to systolic arrays. You have multiple instructions that operate on single data element. Basically, you feed a single data element, and then different instructions operate on it until you get the results. This is very similar to a systolic array, and I'll show you a picture, somewhat similar, a generalized picture soon. So the closed form is really a systolic array streaming processor. And finally, MIMD, you have essentially multiple instructions or multiple instruction streams operating on multiple data elements. You can think of this as a multiprocessor or a multi-threaded processor, essentially. And these are 4 different types of paradigms. These can be combined with each other. You can have a processor that has all 4 of these inside. Now, some systems, some SoCs today actually have that today. Like the Apple M1 has all of them, I believe. Okay, so if you're interested, you can look at this paper. The terminology is a little bit different, but I've given you the gist of it. So this is the example that this paper gives in terms of what is MISD, multiple instructions operating on single data. You have data storage, you bring the data, and then you have some processing elements, operates on the data, passes the, let's say, modified data to the next processing element, pass the modified data to the next processing element, etc. So it's very similar to a systolic array, like we've seen yesterday. So that's a generalized systolic array. Because you could, as I mentioned yesterday, these systolic execution, these processing elements can be programmable using instructions as well. Okay, so if you haven't attended yesterday's lecture, that's yesterday's lecture. And this is SIMD we're going to cover today. And if you look at this picture that is provided in that paper, you have this instruction unit. Instruction unit sends the same instruction to different data elements, essentially. So these different execution units get different data elements from the operand stored. This doesn't make it very clear, but we're going to make it clear soon. And this is similar to what we're going to call an array processor. And these processing elements, functional units, have very limited communication between them. In fact, we'll see no communication initially in our processors. Does that make sense? Okay, so these are the paradigms, essentially. So we're going to look at the SIMD paradigm. And I mentioned that SIMD exploits data parallelism. And what does this mean? Essentially, so far we've been always exploiting concurrency, right? Different sorts of concurrency. Out-of-order execution, for example, exploits concurrency that's irregular. It builds a data flow graph and tries to figure out which one can be executed. You're really trying to find which instructions can be executed concurrently. Here in SIMD, the type of concurrency we exploit is fundamentally different. It arises from the semantics of the program performing the same operation on different pieces of data, essentially. That's why it's called single instruction, operates on multiple data. An example is dot product of 2 vectors, or whatever you do on vectors actually applies nicely. That's why one of the processors is going to be called vector processors. Now, contrast this with data flow. In data flow, concurrency really arises from executing different operations in parallel in a data-driven manner. Basically, data gets available, it actually fires an instruction, and these instructions have no relationship to each other that are fired, except they happen to have their data ready at a given point in time. It could be completely different instructions, basically. Contrast this with thread parallelism at a higher level. This is multiple instruction, multiple data. The concurrency arises from executing different threads of control in parallel, different tasks in parallel. And again, these may have nothing to do with each other. But we're going to get back to GPUs because GPUs are going to combine SIMD and thread parallelism in a very particular way soon. Okay, basically SIMD exploits operation level parallelism on different data. Same operation is concurrently applied to different pieces of data. This is really still a form of instruction level parallelism because you can think of these operations as instructions, except an instruction is combined, collapsed, such that it applies to many, many different pieces of data. Right? Basically, instruction happens to be the same, meaning that you don't need to decode the same instruction many, many times. So imagine that you're actually adding 2 vectors of 1 billion elements. In a scalar processor, you would be decoding the same instruction, add instruction, 1 billion times, fetching and decoding. In this case, we're going to see you fetch and decode the add instruction only once, and it's going to control 1 billion data elements to be added. So that's where the efficiency really comes from. You basically don't waste time figuring out, oh, I'm doing this operation. Basically, you know that you're doing this operation on 1 billion data elements, so you're not going to waste time figuring out what you're going to do to all of those elements. You're going to do that only once. So you're basically amortizing the cost of control because you're doing the same thing across billions of elements, right? So that's the beauty. So if your vectors are larger, this becomes more efficient, as you can see, right? If your vectors are smaller, this starts resembling a scalar processor. In the limit, if your vectors are size 1, meaning a single element in each vector, this is a scalar processor. Right? Okay, so basically, this is what we discussed. This is a processing paradigm. A single instruction operates on multiple data elements, and this can be done in time and space. Actually, a lot of things can be done in time and space. We can revisit some of the discussions we have had for earlier paradigms in terms of time and space, but here it fits very nicely. Basically, we're going to have multiple processing elements, for sure, execution units, just like we've been having so far. And we're going to explore this time-space duality in how do we handle the vectors. So in an array processor, the same instruction operates on multiple data elements at the same time using different spaces or processing elements, if you will. So you have an array of processing elements that can do the same thing, and a single instruction instructs them to do exactly the same thing concurrently at the same time to all of those data elements, different data elements. We're going to see this picture also. Vector processor, on the other hand, is more frugal in the sense that you don't need to have many different processing elements that do exactly the same thing. You can have only one, but you reuse that processing element in time. Every single cycle, you do the same operation on different data elements in consecutive cycles. Basically, the same instruction operates on multiple data elements in consecutive time steps using the same space processing element. This is why vector processors were initially more popular, because they were more hardware efficient. You don't need to replicate the same functional unit many times. You can just have one add unit, and a vector operations can be pipelined through it. But then array processors became more popular as we could put more transistors on a chip. Today's processors are a combination of both. If you look at a GPU, it's not a vector processor, it's not an array processor, it's a vector and array processor, basically. And we will see that also. Basically, you can do both time and space type of processing. So before I show you this time-space duality, I need to define one more thing because I think this is important. Basically, we're going to operate on vectors, right? We're not going to operate on scalar values. So far, we've been operating on scalar values, and these scalar values are stored in registers. And whenever we access a scalar value, we say register 1. Okay, and register 1 gives us one element. Now the question is, how do you get many elements, right? If you're going to operate on many elements, your registers also should store many elements. Essentially, instead of having a scalar value in a register, we're going to have vector registers. So each vector data register holds n m-bit values. N is the vector length or maximum vector length you can have in an instruction. Each register essentially stores a vector. So this is register V0. We're going to call it V0 because vector register is 0. In fact, I'm going to call it VR0 in the next slide. V1 is another vector register. V2 is another vector register. So not a single scalar value as we saw before. You can see that this is V0's 0th element, V0's first element, and V0's n minus first element. Right? And then you feed the processing element one by one. Every clock cycle, you feed it with one element. And the processing element can be pipelined, as you can see, right? And these are completely independent operations. You're adding, for example, V0 to V1. Clearly, the operations that happen on different elements, vector 0's 0th element plus vector 1's 0th element, is independent of vector 0's first element added to vector 1's first element, right? So it can deeply pipeline this, whatever functional unit it is. It could be square root, your favorite functional unit. So this is the idea, basically. This is the idea of a vector register, and the result is stored in a vector register. The 0th element gets stored in vector, the sum of these 0th elements gets stored in destination register V2's 0th element. Okay? So just extend the scalar value to a vector value. And this is our simple vector program to illustrate the difference between an array processor and a vector processor to begin with. So this is our instruction stream. It's also something very simple, basically. It's a 4 element array, A. You first load it from memory into a vector register. I didn't name the vector register, just one vector register, whatever, because that's the only thing we're going to use actually. And then we add 1 to each element. This is a vector add. Every element is incremented by 1. And then every element, after being incremented by 1, multiplied by 2, as you can see. So there are dependencies clearly. And then we store the resulting elements into the array again, into memory. Okay, so this is basically our scalar Actually, you can take the scalar program and just vectorize it, right? That's the idea. Okay, let's see how this executes on an array processor versus a vector processor. Vector length in this case is 4. I'm going to define that more formally soon. But basically, an array processor can do the same operation across multiple processing elements at the same cycle, in the same time, basically. So all of these processing elements are capable of executing all of these instructions. So these are beefy processing elements, expensive. So in the first cycle, we can execute 4 loads. Now, what does this mean? We're basically loading element 0 from memory into vector register 0th element in this processing element. Element 1 from memory into vector register element 1 in this processing element. And then element 2 here and element 3 here. Okay, concurrently. Now it looks beautiful. And we're done with the instruction because we have parallelism, right? And then we take element 0 and increment it by 1 in this processing element, element 1 and incremented by 1 in this processing element, and element 2 and element 3 concurrently again. And then multiply each element by 2 concurrently in different processing elements. And then do the store of the resulting value concurrently to different locations in memory, consecutive locations in memory. Makes sense, right? So basically, this is beautiful, and this is the fastest you can get this program using this paradigm, if you will. Okay, so let's take a look at how vector processor does it. Vector processor is frugal, as I said. Processing elements are simpler. You have only one load element, one processing element that can do add, one processing element that can do multiply, and one processing element that can do stores. So you don't have this luxury, if you will. So you have to perform consecutive operations on consecutive elements in time, right? So this is in the first cycle, you start loading the first element from address A to the vector register 0th element. In the next cycle, you load element 1, okay? Concurrently, this result is done, hopefully, and you can add 1 to it, right? So you're operating on 0th element and adding 1 to it in the add unit. And then in the next cycle, you're loading the second element in the load unit, adding 1 to the first element in the add unit, and multiplying the 0th element by 2 in the multiply unit. And then this is the steady state, if you will. You're loading the third element, adding to the second element, multiplying the first element, and storing the 0th element. And then you keep doing this. Okay, you can see that vector processor takes longer because its resources are, let's say, more frugal. It's not as expensive as an array processor. But this is the time-space difference. If you look at a vector processor, you do the same operation at a given time. And this is the time axis over here, and this is the space axis. But if you look at a vector processor, you do different operations at a given time, right? And in the steady state, you're still doing 4 operations. But that steady state may take some time to reach the vector processor, as you can see. Okay, so if you look at the space, you do different operations in the same space in the array processor, whereas vector processor, you do the same operation in the same space, which is really the huge cost efficiency of a vector processor. That's why vector processors have been really popular until we were able to actually increase the functional units significantly in our systems. Okay? So as we will see later on, we're going to combine these at the end of this lecture, and GPUs will combine both. Okay, so now let's contrast this to VLIW. Yesterday, I showed you this picture. We looked at VLIW. We had a single program counter that would fetch a long instruction word, right? Multiple independent operations are packed together into a long instruction. And these independent operations had nothing to do with each other, right? Okay. Array processing, let's just look at array processing in this particular case. If you look at a program counter, it specifies a single operation, except the single operation gets expanded to multiple different data elements. So this is the contrast between VLIW and an array processor. VLIW actually can exploit more general purpose parallelism, as you can see, as long as it's discoverable by the compiler and packable into instructions like this. VLIW guarantees that these can be concurrently executed. Array processor also guarantees that this instruction specifies 4 operations, in this case, vector length is 4, that can be concurrently executed because they're independent of each other because of a different semantic property. In the first case, the compiler, in VLIW, the compiler guarantees that these are semantically independent. In this case, yet again, the compiler or the programmer guarantees that these are operating on different data values, right? So in this sense, they're similar, but similar in the sense that they're doing multiple operations per cycle, except the relationship between the operations in this case is you're doing the same operation, single operation on multiple different data elements. Makes sense, hopefully, right? And we're going to see that VLIW was actually developed to fix the problems that array processors is having. I'm going to read a part of the VLIW paper that is very, let's say, not harsh, but realistically hard on an array processor. Unfortunately, array processors have been quite successful, but VLIW has not. Because it relies on some parallelism that's a lot harder to discover. Even though it's much more general purpose, no question about that. This is much more general purpose, as you can see, right? But this is much harder to do from a compiler or programmer perspective. And this is much easier if your problem fits. This parallelism exists in all images, all videos. If you're doing the same operation on many, many images or many, many parts of an image, you have millions of pixels that you're operating on, right? That's your vector, basically. Whereas this one is, Okay, so VLIW back. We'll get back to VLIW. Now let's talk about vector processors in a little bit more detail. I'm going to start with vector processors, but everything I say is really applicable to array processors. It's just you just need to expand it in space as opposed to time. So what is a vector? Vector is really a one-dimensional array of numbers. This is a math definition. And clearly many scientific and commercial programs use vectors. There are many of them. That's why people have developed SIMD extensions that we're going to talk about at the end of this particular lecture. But let's look at this example. This example averages 2 vectors, right? It basically takes the element-wise average of 2 50-element vectors. A and B are both 50-element vectors. At least you're working on 50 elements at a time and storing the average into the C vector. So a vector processor is one whose instructions operate on vectors rather than scalar values. So you take vector registers, essentially. So there are some basic requirements for this. Let's define these. Clearly, vector registers. That's why that was important to define even before I defined array processors and vector processors. You need to load and store vectors. You need vector registers. And these clearly contain vectors. Okay, sounds good. Now, I've kind of introduced the vector length register. You need to operate on vectors of different lengths, and this is really why you need the vector length register. There are instructions that set the vector length register so that you can say, oh, at this point, I'm operating on vectors that are of length 4. At this point, I'm operating on vectors that are of length 1000. There's clearly a maximum vector length, and that's really determined by the number of elements in a vector register, right? It could be 64, for example. We will see in Cray it's 64, but it could be much larger as well. Now, GPUs are nice. They eliminate this vector length. It's easier to program. Okay, so, and then there's a vector stride register. This is something I'll introduce. How many of you know the notion of stride? Okay, good. You're going to learn something again. So basically, elements of a vector might be stored apart from each other in memory. And vector stride register denotes how far apart from each other. They should normally be stored regularly apart from each other. Irregular storage, we're going to handle later with some different types of instructions, which we're going to introduce later. But basically, stride is the distance in memory between 2 elements of a vector. And we're going to see why this changes. Stride is not always 1. If it's 1, actually, it's nice. Basically, consecutive elements of the vector that you're operating on are actually stored in consecutive locations in memory. This actually has a lot of benefits, as we will discuss. But your stride is not always 1. And I'll show you a very basic example. Matrix multiplication, our favorite program these days. Right? So let's take a look at A and B matrices. Both are stored in memory in row major order. Do you know this terminology, row major? Column major? No? Okay, you're going to learn more. But basically, row major order means that consecutive elements in the same row are stored in consecutive locations in memory. Column major means exactly the opposite. Consecutive elements in the same column are stored in consecutive locations. And this has a huge implication in terms of locality, prefetchability, caching, etc. We're not going to deal with that. We're going to talk about stride. So let's take a look at two matrices that we're going to multiply. This is A matrix. This is A0 element over here. This is the B matrix. This is B0 element. They're in row major order. So the first row of A0, is stored in consecutive locations, as you can see. The first element is in location 0, the next element in location 1, the next element is location 2. These are offsets from beginning of A, of course, right? And then the first element in the next row starts from location offset 6, right? And if you look at B0, matrix B, the first row is very similar. It has 10 elements in a row, and they're stored in consecutive order. The next row starts from offset 10. So clearly, this is what they look like, basically. I didn't show the entire thing over here because I don't have space, but A starts from some location, and these are the offsets of the elements, where they are, and this is what they correspond to in the matrix. B starts from some location in memory, and these are the offsets of the element, and this is what they correspond to in terms of the visual structure of the matrix. So clearly, A is a 4x6 matrix, 4 rows by 6 columns. B is a 6x10 matrix, and you can multiply them because these 6s match, right? And you get a result C of 4x10. Now, let's take a look at how you would do that. So this is basically, to be able to multiply these, what you really need to do is to take the dot product of each row vector of A with each column vector of B. So what you're doing, a matrix multiplication, is really to get one location in the C matrix, you need to take the dot product of this row 0 with this column 0 in B, okay? So let's take a look. To be able to do that, you need to load A's row 0 into vector register V1, or whatever vector register, meaning this A0 through A5, offset 0 through offset 5. And these are consecutive in memory. Each time you increment the address by 1 to access the next column, right? Or next element in the row. Clearly, it's the next column. So this is a case where we have a stride of 1. Consecutive elements are in consecutive locations. The distance in memory is 1 apart in terms of the address. Now, if you're loading B's column 0, that's not the case, as you will see. If basically we want to load B0, offset 0, B10, B20, B30, B40, B50 into the second vector so that we can actually do vector dot product. Now, clearly, they're far apart from each other, right? So each time you need to increment the address by 10 to access the next row, and accesses have a stride of 10 in this case. Okay? So basically, you need to have different stride supports. You can say that, oh, why don't we lay out B in column major order? Yes, you can do that. But what if you start multiplying B with some other matrix, right? You cannot basically have the best of all worlds at a given time. You'll always need to have some support for strides. And this is something that has actually bothered many people. People have tried to develop many ways of overcoming this issue, as we will see later on. But right now, I'm just defining the stride. I'm not talking about why this is good or bad. But stride of 1 can be good because this has better caching characteristics also, as we will see later on. Okay, so that's stride essentially. Now, let's talk about some other characteristics of vector processors. A vector instruction performs an operation on each element in consecutive cycles. That's how we defined it. So because of this, we can pipeline the vector functional units, and each pipeline stage operates on a different data element, essentially. And vector instructions allow deeper pipelines, actually. You can have 1,000, well, if you have a huge vector, let's say, a million element vector, 1,000 deep pipeline is not that bad, right? Because you don't ever flush this pipeline at all. So basically, the main reason is you don't have any dependencies within the vector, inter-vector dependencies. You don't need to check for them. There's no hardware interlocking in the vector. We're talking about pipelining the function units. There's no control flow within a vector. And there's going to be a lot of good things, as we will see. We're going to eliminate a lot of the control flow from a scalar program soon. And there's a known stride, right? You know the stride. This allows easy calculation, address calculation for all vector elements. Like if you go back over here, you always calculate the address by incrementing it by 1 over here, right? Here, when you're loading this column, you always calculate the next address by incrementing it by 10. So you have a known stride, essentially. So that helps actually easy loading of vector registers into vectors into registers, cache, or memory. or even early loading or prefetching, because these are really predictable addresses. We're going to talk about prefetching at one of the latest lectures, but this sort of predictable stride or constant stride helps a lot. But we will see that the address generation unit is essentially you have a base address and then you keep adding the stride to it. Right? And I'm going to show you an example of that. Everything is clear so far? Now it's beautiful, right? As you can see. All of these things are good for designing a high performance processor. Heavily pipelined, no dependencies to check, no control flow. What else you would ask for? You should ask for basically large vector lengths. If your vector lengths are smaller, then these unfortunately do not work very well. Well, basically you cannot pipeline very deep clearly. Well, you can pipeline, but you don't benefit from it, let's say. Okay, so what are the advantages of vector processors? Essentially, the lack of dependencies within a vector enables pipelining, parallelization. Pipelining is actually in time, if you will, and then parallelization is in space. So you can actually do array processing as well as vector processing, which is nice. And you can have very deep pipelines without the penalty of deep pipelines, except for, of course, the sequencing overhead, right? And the hardware overhead. I'm kind of ignoring that, but the performance penalty, other performance penalty, like flushing the pipeline, you don't need to do that. Each instruction generates a lot of work, lots of operations, basically. And as we discussed earlier, this reduces the instruction fetch requirements. You don't need to fetch and decode an instruction for every operation. You can amortize the cost of fetch and decode across lots of work, essentially. And this actually leads to high energy efficiency per operation. And if someone asks you why are GPUs energy efficient, this is the main reason, basically. They can amortize the cost of lots of operations across a single control, let's say. Otherwise, there are a lot of reasons why GPUs should not be energy efficient. I can name you many, but because of this, they can actually expose a lot of work without doing a lot of overhead. You're really spending a lot of energy on the computation, if you will. Okay, no need to explicitly code loops, and we will see this very soon with an example. You can have very few branches in the instruction sequence because we're going to eliminate branches. Because if you think about a scalar program, what you do is that you loop and you do the same thing on many, many elements of a vector, right? Now we're going to specify this as you do one operation on a vector and then the next operation and then the next operation, and then branch is only one thing at the end that you do after 1 million operations, let's say, per vector. And you have a highly regular memory access pattern because of the strides that we have looked at earlier, and this is going to benefit us soon. Of course, there's a disadvantage. Like every idea, we have downsides and upsides, and the huge downside of vector processors is it doesn't always work, right? It works if parallelism is regular, data and SIMD parallelism. If you can fit your parallelism to this paradigm, it works nicely, meaning vector operations. But unfortunately, it's very, very inefficient if parallelism is irregular, like some of the programs that we have looked at. If you're searching for a key in a linked list, lots of dependencies, and you cannot parallelize, for example, very well, too bad. So you need to learn, you need to know if you can vectorize the program. We're going to talk about vectorizable loops. So your loops need to be vectorizable for this to work. And this is exactly why the VLIW paper says this. To program a vector machine, the compiler or a hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. That's hard to do in the first place and just as hard to change. One tweak and the low-level code has to be rewritten by a very smart and dedicated programmer who knows the hardware and often the subtleties of the application area. And this is actually a very nice description of why some applications don't fit vector processors. But if they fit greatly. If they don't fit, these problems happen. And Josh Fisher poses VLIW as a solution to this, but it has its own problems, as you know, right now, right? And if he continues, often the rewriting is extremely difficult, et cetera, et cetera. Okay, and that's the recommended paper. You can read more about it. Okay, so we should, before moving on, we should actually not get too excited because there's Amdahl's law, which you have reviewed, and we looked at this before. Basically, vector processing works well in the parallelizable fraction of the program, right? In the serial part, you don't have a lot of data parallelism. In the parallelizable fraction, ideally, you should be able to speed up with the number of processing elements that you have. So this is Amdahl's law. Amdahl's law says that the parallelizable fraction of the program can be sped up by n, assuming you have n processors. Even this is ideal. If you take the advanced architecture course, we're going to talk about why that's ideal. But assume that this is true for now. As n goes to infinity, this goes to 0. So your speed up at the limit as n goes to infinity is really bound by f, which is a parallelizable fraction. If your parallelizable fraction is 50%, your speed up is at most 2. That doesn't sound good now, right? With infinite number of processing elements, your speed up is only 2 if your parallelizable fraction is 50%. So your parallelizable fraction needs to go up very high if you really want to benefit. If it goes up to 99%, now your maximum speed up is 100, right? If it's 99.9%, it's 1,000. 99.99%, it's 10,000. That sounds great now. Now we're talking. But the problem is 99.99% is very hard to get, right? Basically, that means that you need to do very, very little work in serial part of the program. And serial part of the program can be just distributing tasks to many, many processors, right? And that can take time, right? You need to really, really minimize it. So that's why Amdahl's law is so strong. So basically, that's what this says. Maximum speed up is limited by serial portion. This is called the serial bottleneck. And this serial bottleneck term especially came about because of vector processors. People basically said, oh, we have the serial bottleneck. What do we deal with it? As we will see, Cray's solution was to actually design the fastest scalar machine of its time. Cray designed the fastest supercomputers. They were actually fastest vector processors, and they were also fastest scalar processors at the time, so that they could get out of the serial bottleneck very quickly, as much as possible. So basically, all parallel machines suffer from the serial bottleneck. Whenever you're parallelizing code, it doesn't matter how you're parallelizing it, you suffer from this. Okay, that's why this paper was read earlier, right? And how many people did this review? Or you don't remember? Some people, okay. Maybe it's been so long that you don't remember. Okay. Okay, so this sort of issues actually are really, really interesting. And this is not the only thing. This is a lecture from our computer architecture course where we discuss a lot more, because it's not just about the serial bottleneck. I'll give you just some critical thinking. This f divided by n is not true also. In single instruction multiple data processing, f divided by n is actually relatively true, because you're really parallelizing the operations concurrently across multiple data elements. And that's the closest you can get probably to f divided by n in SIMD processors. But we will see a lot of other issues. Okay, and if you're interested, you can look at those lectures right now. Okay, so that was one limitation, basically a parallelization. If you cannot fit your application to vector processors, you suffer. You don't get benefits. And Amdahl's law is one reason why you suffer. There could be other reasons why you suffer, because you could not really get to a parallelization level with your programming skills, right? And GPUs actually suffer from this also. If you want to program a GPU, you'd better be an expert to actually maximize your parallelism. Okay, another limitation or downside is, as we will see, memory bandwidth can easily become a bottleneck, especially if you don't have balance between compute operations and memory operations. And especially data is not mapped appropriately to memory banks. We're going to talk a lot about this actually starting today, but we're going to see memory structure a lot more. But one of the major reasons, major places where memory became a bottleneck first was really vector processors, because these are pushing the limits, right? You're really, with one single instruction, you're unleashing so many memory operations, right? I want to load a billion elements from memory. How does your memory system support that? The most sophisticated memory systems initially were in vector processors, and we're going to talk about some of those ideas. But now, of course, they're in all processors today. Because, yeah, we're executing all sorts of code today in all processors, essentially. Okay, so let's go into vector processing in more depth, unless there are questions. Okay, so we're going to talk about vector data registers a little bit more. We have essentially each vector data register holding n-bit values. And you can see that you have the vector register 0, vector register 1. You can have a vector register set, essentially, vector register file, as we have seen. And then we have vector control registers, vector length, vector stride. We already talked about this. And then I'm going to introduce vector mask, because you should be able to do conditional operations on vectors. Meaning, if you have a vector of, how do you basically do conditional operation on a vector? If something is true, increment this value in this element. Otherwise, do not increment this value, for example. Basically, you have a vector mask register that says, that computes a mask as to whether the operation should be done on the vector or not. And then based on that mask, you apply the operation to the vector. And if the bit in the mask is 1, the operation is done. If the bit in the mask is 0, the operation is not done. This is a form of conditional execution or predicated execution. And this was also developed in vector processors first, and then they went into other high-performance processors, but they were not very successful in other high-performance processors. Okay, so we're going to get back to this. We're going to see how to program using vector masks. So maximum vector length can be n. This is, as I said earlier, maximum number of elements stored in a vector register. And you can see n over here in these vector registers. Vector mask register, VMask, indicates which elements of a vector to operate on. And this is set by vector test instructions. This is very similar to compare instructions in scalar ISAs. For example, here we set every element of the vector mask by comparing every element of a vector register k to 0. Now, what is the result of this operation? If the element I of vector register k is equal to 0, then element I of vector mask is set to 1. Otherwise, it's set to 0. Okay? So basically, this is a bit vector. This is a bit vector specifying whether the condition that you tested was true for each element of the vector. And then you can use this to perform conditional operations, essentially. After this, after you set the mask, if you do a vector add, the addition will take place only for those elements where the vector mask, with the corresponding element of the vector mask is set to 1. Okay? So it's beautiful. We're going to get back to this. Now let's look at the vector functional units a little bit more. Essentially, we feed data from vector registers into 2 ports of the vector functional unit that are pipelined, as you can see. And eventually the results comes out, and each element in a pipeline manner gets to the next vector register, to the destination vector register. Right? This is the operation. Here I'm kind of pictorially depicting vector 1 multiplied by vector 2 stored into vector 3, register 3. And in this case, we're looking at a 6-stage multiplication pipeline. Right? After 6 cycles, the first element result is available and placed into the destination registers, or 0th element, I should say. The 0th element result is available, and it's placed in the destination register 0 element. And every cycle, because of the pipeline, you get 1 element per cycle. Right? Initially, you fill the pipeline, but you get 1 element per cycle throughput from the functional unit. Based on all the pipelining principles, this is true, right? And here, the control of the steep pipeline of the functional units is simple because elements in vector are independent. Okay, good. And this is an example of a real machine, Cray1. You can actually see a version of this in the CAB building. How many of you have seen it? That's the yellow machine. Okay, good. Have you operated it? I don't know if it's operational. It's old, as you can see. But let's take a look at what this entails. So a vector processor is not ever a vector processor. Only a vector processor, I should say. It's also a scalar processor. Because you need to do both operations, right? As you can see over here, there's a vector unit, vector registers, similarly to what we have described. And this particular processor had 8 64-element vector register. Each element had 64 bits. You can see that for its time, this is actually pretty powerful. At very similar times, we were talking about 4 bits, 8 bits in microprocessors, right? And the goal was really to do supercomputer type of applications, right? Scientific simulations, etc. Okay, 16 memory banks. We're going to talk about that. So memory needs to be heavily banked so that you can actually get 1 element per cycle from memory. How do you sustain 1 element per cycle is important for vector processor. For array processors, you need more than 1 element per cycle from memory. Okay, for vector processor, we start with 1 element per cycle. But this also has scalar registers. So there's actually a scalar unit over here. You can see that it has 8 64-bit scalar registers, very similar to a scalar ISA like MIPS we have seen. And then there's also an address unit that does address computation and address registers. And then there's a floating point unit at the time also. So it's a pretty beefy processor for its time. And it's actually, well, it's actually multiple chips because of times, right? 1970s. But it's a processor overall. And you can see that it's very heterogeneous. So heterogeneity is really built into this processor to begin with. But the main core is really the vector processing part that does hopefully most of the computation. If you're doing computation here, you're really exercising the serial bottleneck. And that's why these folks designed this scalar processor to be the fastest of its time. which is fascinating, right? You should be doing operations always here, but when you go here, you got to get out quickly. So design the scalar unit to be fastest. Okay. Okay, that's the importance of Amdahl's law. Okay, so if you're interested, you can actually read this beautiful paper that describes the Cray-1 system. And this is the machine that you may have seen and you may have read about it. I'm not going to talk about it. This is a block diagram of the same thing in a nicer way, let's say. I think you can actually find information of that. Maybe there's a booklet over there. Maybe I'm remembering some other place. There might be a booklet. Okay, so you can read more about it. Cray basically has designed many vector processors. It's not that important in terms of what they've designed here, but it's important historically. And they have a lot of functional units, as you can see. Let's take a look. Basically, these are address functional units, scalar functional units, vector functional units, which we're going to talk a lot about today, but there's also floating point functional units, as you can see. And they specify the time in terms of clock periods, right? Vector functional units, for example. Yeah. Okay, there's more. And you can see that the memory is actually important and I/O is important. So it's a full system, essentially. We're going to see more of this later. Okay, I'll give you some story over here, which actually gives the idea of Amdahl's law really nicely. Seymour Cray was a very principled designer, if you will. He was the early designer of the supercomputers. And he asked this question, which is always good to think about. If you're plowing a field, which would you rather use? 2 strong oxen or 1,024 chickens? And this is a fundamental problem that keeps coming up, right? Do you use 2 powerful single-core processors, or do you use millions of powerless, simple processors? And the answer is, it depends, right? As always. Basically, maybe plowing a field, these guys are better. They know what they're doing, and they're higher performance, right? And they can be a lot more energy efficient also, as we've discussed yesterday, right? Because they finish the job much earlier, whereas these chickens will run around and they will never finish the job. So you'll be expending energy on the chickens forever. And then eventually you decide to eat them, maybe, I don't know, maybe not. But basically they will never finish the job, right? Okay, so this is the joke of it. So it's good to think about this picture when you have a problem at hand, right? What do you use? What kind of processor do you use? Vector processors, try to do this, and heavy out-of-order superscalar processors may be trying to do this, right? Anyway, but Seymour Cray was a smart person, or the designers of early supercomputers were smart people, so they actually designed both. They wanted to have both chickens as well as the strong oxen. Okay, let's talk about memory banks, because this is going to be important. How do you load and store vectors from and to memory? And this requires loading and storing multiple elements. You don't want just a single element. We want many elements, and we want to sustain a throughput, right? We saw that the throughput of the functional units can be 1 element per cycle really easily. Now, how do you ensure that memory gets you 1 element per cycle? And every cycle, because we're going to be loading millions and billions of elements potentially, right? So elements are separated from each other by a constant distance. We're going to assume this initially. This is called a stride. If this is not true, it's going to become a bit harder, as we will see. We're going to assume a stride of 1 for now, for simplicity. Later, I'm going to generalize this. And basically, elements can be loaded in consecutive cycles if we can start the load of 1 element per cycle. So basically, every cycle you start the load of 1 element, and hopefully you get the result after n cycles. N is the memory latency. Memory latency is hard to reduce for reasons we'll discuss later. So we should be able to start 1 element per cycle and get 1 element per cycle, 1 memory operation per cycle, and get 1 element per cycle every cycle, essentially. So that's basically our goal. So the problem is, how do we achieve this with a memory that takes more than 1 cycle to access? Right? If you have a monolithic memory system, you ask memory, give me 1 element per cycle. Let's say 11 cycles later, it gives you 1 element. But during these 11 cycles, it's busy. You cannot give it another request. So you need to wait for 11 cycles. So if you have a monolithic memory system with a single port, your throughput is 1 element every 11 cycles. So now how do you get to 1 element per cycle if your memory is 11 cycles, let's say? And the answer is really banking the memory. Of course, you can say, add more ports to memory. Yes, and that's expensive. You can basically have lots of ports, 11 ports, so that you can start 1 element per cycle such that once you get the first element you started, you can start the next one because one port will become free. So you need 11 ports essentially if your memory is 11 cycles. But another solution is banking the memory, which is a cheaper solution, and interleave the elements across banks. And we're going to use this solution. And we're going to look at that again. So if you missed this today, which hopefully you won't, we're going to see this again when we talk about the memory systems. But this is the idea of memory banking. So remember, we had memory address register and memory data register, and we assumed memory is monolithic. Now we're not going to assume that. We're going to have 16 banks in this particular case, and have a memory address register for each and a memory data register for each. But we're going to have a shared data bus and shared address bus across those, because these are actually very, very expensive. So if you think about memory, this is really the memory chip. Well, I guess this is the memory chip boundary. I should have had that over here. And this is the CPU boundary. And they communicate with each other with the address and data bus. And increasing the size of the address and data bus, it actually hurts your cost a lot, because these actually add pins to the chips. And if you add pins, your cost increases. In this case, we're not going to add pins. We're going to start or send one address per cycle. It's going to target one particular bank. And then we can get one data element per cycle from the MDR, only from one particular bank. But we should be able to send one address per cycle to different banks. That way we can start the operation or the memory access of a bank in the first cycle. And then if we need data from the next bank, we can start the memory access from that bank in the next cycle. We can start the memory access from the next bank in the next cycle. So we can actually start memory accesses, one memory access per cycle from different banks. And if each bank takes 11 cycles, you just need 11 banks, right? But of course, 11 is not a great number to distribute your addresses to, because our addresses are fundamentally powers of 2. So that's why I have 16 over here. Okay, so basically memory is divided into banks that can be accessed independently, but banks share address and data buses to ensure that memory chip pins are not increased. We're going to talk about that a lot when we talk about memory design next week. We'll start next week. This way you can start and complete one bank access per cycle. That sounds good so far. But under what conditions becomes an issue? We'll talk about that. Basically, under this condition, you can sustain n concurrent accesses if all n go to different banks. So I'm going to finish the vector memory system, and then we're going to take a break. We're almost done. Basically, if you look at a vector memory system, you have the next address is previous address plus the stride. So address calculation is very simple. You have a base address, and then add stride to it, and that's your next address. And then you keep adding stride to the next address that you generate. And every cycle you latch it. Initially, you start with the base address. Hopefully, that goes to this bank. You increment it by stride. Hopefully, it's 1, let's say. That goes to this bank. In the next cycle, you increment it by the stride. That goes to this bank. And then this bank, this bank, this bank. So consecutive accesses go to consecutive banks. As a result, you can sustain one memory access per cycle and one element per cycle. But this, of course, requires what I just formalized over here, right? If your stride is 1, and consecutive elements are allocated to different banks. In other words, in memory terminology, consecutive elements are interleaved across the banks, and number of banks is greater than or equal to bank latency. Then you can sustain one element per cycle throughput. If any of these is not true, this equation gets broken and you cannot sustain that throughput. And I'm going to generalize the stride later on. Stride 1 is nice, but stride 1 is not enough. If consecutive elements are all in the same bank, somebody did not do the data mapping well, too bad. You're back to one element every 11 cycles. And this is what Josh Fisher was talking about in that paper. He was saying, if you don't have the programmer knowing where to map the data, you're going to get a terrible result. And that terrible result could be one element every 11 cycles, right? So data mapping this is what is being referred to. It's not really mapping of operations to functional units. It's really mapping of data to memory banks. And if you mess this up, everything else is messed up in a vector processor, including a GPU. If you're programming a GPU, how many people program GPUs here? Okay, you know the importance of this, probably. Data mapping, somewhat. Okay, depends on what kind of performance you want to get. If you want to get the highest performance, this is really extremely important. And we will see this soon again. Okay, this is a great place to take a 10-minute break. So we're going to be back at 25 past, and then we're going to actually go through this code and execute on a vector processor. But this is scalar code, so we're going to see the scalar execution first. There were some good questions about programmability of systolic arrays and how much performance you would get. We did not cover a lot of programmability issues, but even for systolic arrays, if you really want to get high performance, you need to orchestrate your data, as we discussed, and make sure that you actually fit your matrix operations in a pipeline manner into this matrix unit, if you will, that we discussed with TPU, for example. So programming these more specialized or different paradigms is not as easy as programming the von Neumann architectures that we have seen. Okay, so now that we know about banks, don't forget about the banks. Let me go back actually just to remind you. So just to make things a bit more clear over here, we're dividing a monolithic memory into 16 pieces, right? So imagine the memory that we kind of thought as monolithic. It has 2 to the n locations. We're dividing it into 16 different pieces. So this has 2 to the n divided by 16 locations. This has another 2 to the n divided by 16. This has another 2 to the n divided by 16, ... right? So each piece has some part of the memory, main memory. And now we need to lay out the data such that we can sustain one access or one element provided by memory per cycle. And for that, you need essentially these to be satisfied. If stride is 1, consecutive elements need to be interleaved across banks, and number of banks need to be greater than equal to bank latency. Then you can sustain one element per cycle throughput. And this is what I'm going to assume when I say you have n banks, if you will. Okay, but now let's start with an example of the benefits, at least the performance benefits of a vector processor. And this is some scalar code. And we're going to look at the performance of the scalar code on simple machines first. And this is the element-wise average that I showed you earlier. If you actually write this element-wise average loop in scalar code, you write a loop, basically, right? And this shows each instruction and its latency in clock cycles. So this is, you basically initialize 50, the loop boundary, and then addresses of A, B, and C into registers. And each of them take 1 cycle. So this is the loop initialization. And then within the loop, what you need to do is load one element from array A and increment the address with which you load from array A. And here we actually combine multiple instructions using an addressing mode called auto-increment addressing. If you actually are always incrementing the address by 1, while you're using the old address, or value of R1, you also increment R1, basically. So this instruction does multiple things. It loads the memory location specified by R1, which is really the address of A initially, and then it increments R1 by 1, so that you go to the next element in the vector. We're assuming that the elements are stored consecutively. Right? So that way you load the first element from vector A, and then you load the first element from vector, or 0th element, I should say, 0th element from vector A, 0th element from vector B. Each of these take 11 cycles, as you can see. And then you add them up. So there's a dependence between these two, and put the results into R6. These are scalar code. There's no vector happening over here. There's no vector code. This takes 4 cycles. And then there's a dependent shift. You shift it by 1, meaning divided by 2. 1 cycle, assume that. And then you store the result of the shift operation to the memory location specified by C into element 0 to begin with, and then you increment the address by 1. Okay? So that takes 11 cycles. And then there's this monstrous decrement and branch if not 0 instruction, which is a nice instruction. You decrement R0 and branch if it's not 0, meaning keep iterating the loop until R0 becomes 0, right? So you count down from 50 to execute this on every single element. And this takes 2 cycles. Okay? So this is what you would do in a scalar processor, right? You could write it this way. And we actually saved some instructions, as you can see, using auto-increment addressing. We don't have these instructions. We have a relatively special purpose branch, etc. And this is also auto-increment, by the way. Okay. So if you look at this, you execute 304 dynamic instructions, right? This is a lot. We will reduce it down to 7 with vector code. It's going to be beautiful from that perspective. So it's going to be nice from the energy efficiency perspective. But before we get to this, let's do some rough analysis in terms of how long it takes to execute this code on a scalar processor, in-order processor with one bank. Monolithic memory, basically. Essentially, if you have monolithic memory, first two loads in the loop cannot be pipelined. So each of them takes 11 cycles. And roughly, the entire loop takes the sum of these cycles over here. So it's really 22, 26, 27, 29, 40 cycles. You could potentially pipeline this branch, but eventually you need to resolve it. Okay, let's take 40 cycles for the loop. And you do the loop 50 iterations, so it takes 2,000 cycles. Initially, you need to initialize these instructions. So it's 4 instructions. So it takes basically 2,004 cycles. Okay, we're going to reduce this with vector processors. But you could reduce this actually if you have a in-order processor with a better memory system. Let's take a look, in-order pipeline processor. So scalar execution time on an in-order processor with one bank, but 2 memory ports, such that 2 different memory accesses can be serviced concurrently, or 2 banks where arrays B and C are stored in different banks. Okay? No, that should be A and B, right? Okay. What happened? Okay, I'm fixing online. Okay, because A and B, those are the things that we actually load with the load instructions. Where are we? Okay, so basically A and B are in different banks such that you start the first load in the first cycle, and then you start the next load, pipeline the next load in the next cycle, such that both of the loads together take 12 cycles, right? One of them takes 11 cycles and the other one takes 1 more cycle after that, right? But then you cannot parallelize anything else because everything else is dependent afterwards, if you remember this code. So basically these 2 together take 12 cycles now, and then 16, 17, 29, 31. Okay, sorry, I missed something over here. 30, I think, right? 12, 16, 17, yeah, 19, 30. Okay, that's better. So 30 cycles. You could potentially do some more pipelining, but it's not going to significantly reduce this. But without going through the machine details too much, it takes about 1,500 cycles, right, total. Okay. Now we're going to reduce this with vector processors. Of course, out-of-order execution, etc., can help you a little bit more, right, if you have a larger window. But in this case, out-of-order execution is not that great because everything in the loop, except for this branch, and these 2 loads are independent, but there's a dependence chain over here, right? The next iteration of the loop is independent. Of course, out-of-order execution enables you to go to the next iteration of the loop, so it can parallelize loop iterations. That's one of the benefits of out-of-order execution. But it's going to be expensive, clearly, with out-of-order execution. So you can do more performance analysis, which we're not going to do right now. We're going to compare this to a vector processor. So if you, for this to work on a vector processor, the loop needs to be vectorizable. And what does this mean? A loop is vectorizable if each iteration is independent of any other. And in this case, that's true, absolutely. So if you look at this loop, you will say each iteration is independent because it's operating on different elements, right? So if you really want to program a vector processor, you need to do this loop dependence analysis nicely. If you want to design a compiler that automatically vectorizes, parallelizes code, that compiler needs to do the dependence analysis, and it turns out this is not easy, unless the code is as simple as this, for example. So if you vectorize this loop, this is what the vectorized loop looks like. It's going to be much simpler. This is it, basically. So vector length, our vector length is 50. We set initialize the vector length register that way. Our vector stride is 1 because we laid out nicely our arrays. And then the first instruction is vector load into V0, vector register 0, starting from address A. And this automatically says that load the next 50 elements starting from address A into vector register 0. So how long will it take? The first element will come after 11 cycles, assuming the same memory system. And you get 1 element per cycle in the next consecutive cycles. So basically, this will take 11 plus 49 cycles, right? Vector length minus 1, because the first element comes after 1, and then the remaining 49 elements takes 49 more cycles to come. Okay? So if your vector length was 30, you would basically plug in your vector length over here. Now, if it was actually larger than your vector register length, you need to restructure your program, as we will see later. but it's not that bad. The core of your program will still be this. Okay, this is this instruction. The next instruction is vector load. Basically load the elements of array B into vector register 1. The next instruction is a vector add. Add vector register 0 to vector register 1. Put the result into vector register 2. Again, this is first result will be available after 4 cycles because that's the latency of the adder. And then the remaining 49 results of the addition will come in 49 consecutive cycles, vector length minus 1 cycles. And then next, you take the result of the result that's in vector register 2, shift each element by 1. And this takes, you can see 1 plus 49 cycles, because the first shift finishes after 1 cycle, and then you get 49 other shift results in 49 consecutive cycles. And then the last one is a vector store, which takes the result of the shift in vector register 3 and places it in the memory, starting from the address of C, okay? Which is very similar in terms of latency to the vector loads, as you can see, because it takes 11 cycles to write the first element, and then 49 more cycles to write the consecutive elements. Okay, this sounds good now. And you can see immediately that there's no branch here. We got rid of the branch. And we have only 7 dynamic instructions. 2 of them are setup instructions, and the remaining 5 are actually the instructions that do the bulk of the work. Now, this is where the energy efficiency comes from. You can see that. The control overhead of 300, I don't remember, 14 instructions is gone. And this is a very small vector, right? You're doing this only on 50 elements. Imagine you're doing this on much larger vectors. Okay, so now let's take a look at how long it takes to execute this code. Initially, we're going to assume a very simple vector processor, not even forwarding of data. So this is called chaining in vector processing. I don't like this terminology necessarily, but you will see why it exists. There's no data forwarding between vector functional units. You have to finish all vector length of operations in one functional unit before you can start another operation on the same vector register, essentially. You cannot forward individual elements from one functional unit to another functional unit. Okay, basically the output of a vector function unit cannot be used as the direct input of another. The granularity of weighting is really the entire vector register, if you will. Yeah, basically the entire vector register needs to be ready before any element of it can be used as part of another operation. And we're also going to assume 1 memory port, 1 address generator per bank. This is a good assumption in general, but we're going to fix that. We're going to add more to this later on. And we're going to assume 16 memory banks. In this case, word interleaved, meaning consecutive elements of an array are stored in consecutive banks. And this is going to help us to get consecutive elements in consecutive cycles, clearly, because each bank access latency is 11 cycles. And the first element takes 11 cycles in one bank 0. The next element comes back after 1 more cycle in bank 1. The next element comes back after 1 more cycle in bank 2, etc. Right? So basically, we're pipelining the memory system as well, as you can see, using banking. Okay, so this is the execution time of the code, basically. If you remember, these are the 2 setup instructions. I don't show them over here, vector length and vector stride, 1 cycle each. This is the vector load. So vector load of A into vector register 0. The first element comes after 11 cycles. And because memory system is interleaved nicely and the data is mapped nicely, consecutive elements come in consecutive 49 cycles, right? Serviced in consecutive banks, essentially. And then it wraps around, of course, right? Because you keep interleaving across banks. But because your access latency is 11, your memory bank number should be 16. If your memory bank count was 8, you would have a stall of 3 cycles. You would service 8 requests and then stall 3 cycles, and then you keep doing that, basically. But that's not what we depict over here. Okay, so that's vector load. And because we have only 1 memory port, we cannot start the next load concurrently, because all of these banks are now busy servicing the elements for this vector load, right? So the next vector load can start after at this point. I guess you could potentially schedule it a bit earlier, but I'm making it a little bit easier over here to analyze. Oh. Basically, the next vector load the next element of the next vector load comes after 11 cycles, and the consecutive elements come after 49 cycles. Now, after this data is done, you can start the add operation, which adds vector 0 to vector 1. The first element finishes after 4 cycles. The consecutive elements come in 49 cycles. And then we can start the shift. There's no data forwarding. We're going to fix this with data forwarding. You start the shift in one cycle, the first element comes, and then after 49 cycles, in consecutive 49 cycles, you get consecutive 49 results of the shift. And then the same story, basically. Basically, without doing a lot of effort, this is the result you get, 285 cycles. Now you can say maybe you can start this load earlier and you would be right. You can actually start this load a bit earlier, but it's not going to save you more than 10 cycles, let's say. Okay, so not bad. But now we have a beefy memory system, clear. So we've already reduced the 1500 cycles to 285 cycles, right? And we are also more energy efficient, probably, because we're not decoding a lot of instructions, we don't have any branches, etc. So why 16 banks? Hopefully this is clear right now. We have an 11 cycle memory access latency. Having 16 banks ensures that there are enough banks to overlap enough memory operations to cover the memory latency. And the above assumes unit stride. Basically, that's what we're assuming. And this is correct for our example program. If stride is greater than 1, then how do you ensure you can access 1 element per cycle when memory latency is 11 cycles? Well, then you need to be more careful. We're going to get back to that. Okay, so let's talk about how to improve the performance of this. People are fine with this so far, right? So we're going to improve the performance of this by vector chaining to begin with. So if you look at this, let's take a look at the result of the first element. This is the add, vector register 0, vector register 1. The first element is really available over here. You can actually start the shift right after that and shift the first element by 1, right? But we're waiting for the entire vector register to become ready because we're waiting for the entire vector register. We don't have to do that. We can basically forward this result to the shift unit. And again, similarly shift, we can start the store right after the first element. Basically, we can do element-wise forwarding of results. And that's what we're going to do. That's the idea of vector chaining. It's the fancy word for data forwarding. We're going to forward data from one vector function unit to another. And this is one example over here. You do a load into vector register 1 and forward it element-wise to this multiply unit and forward the result of the multiply unit element-wise to the add unit. So if you look at this, this is vector 1, load unit is loading. And it's also sending the result to the multiply unit. I mean, this is pictorial, of course. In hardware, you need to have muxes, etc., which we're not showing over here. Just like the forwarding that we did for the pipeline processor, right? Basically, this is what you do. Every element goes to this multiply unit in a pipeline manner, such that you don't wait for this entire register to be full. Similarly, the result of this multiplication unit is also supplied to the add unit, every element, consecutive cycles, such that the add unit can overlap execution with the multiply, which overlaps execution with the load. Okay, so while the vector results are coming out, they're coming into these different functional units. And this is going to parallelize the back end of our program. Meaning, actually, after you get the first element of the second load, you can start the shift, this add, right? Because you have the first element of vector 1, you already had the first element of vector 0, you basically add them. And then in consecutive cycles, you get the second element, third element, fourth element, fifth element, up to the 50th element or 49th element, right? So basically, you overlap the latency. You start the vector add right after the first element comes. You start the vector shift right after the first element is produced by the vector add functional unit. And then you can potentially start the store instruction, first element, after the shift is done. But unfortunately, we have a resource conflict over here in the memory. We're going to talk about that. You cannot start this vector store because we have only one port to the bank. That's what we said. So that's why we wait over here. But even if with that wait, even without beefing up our memory system more, this vector data forwarding brought us to 182 cycles from 285. That seems like a good win. And again, if your vector lengths are larger, the benefits are going to be larger. Okay, not bad. Now let's tackle the memory system elements. So we could not parallelize this load and this load, and deficiencies in our memory system actually caused us to wait in the store. So these two loads cannot be pipelined, and this load and store cannot be pipelined. Essentially, we don't have enough ports in the memory system for this. Basically, we had each memory bank has a single port. That was our strict assumption. And this led to the memory bandwidth bottleneck. And we assume that this port is shared by read and write. So we're going to assume now 2 load ports and 1 store port in each bank, more expensive memory system. And this will enable us perfect pipelining right now. So this is basically you start the first load in cycle 1. The second load is completely independent of the first load. It can go to the other port, other load port. So you start the next load. So basically you almost completely overlap the latency of these 2 loads because they access 2 different ports in memory. Of course, 2 different ports is expensive, right? Clearly. 2 different ports is really, 2 different address buses and 2 different data buses. But then, of course, it's shared across banks. But still, it's expensive. But you could parallelize. And you don't have the problem with this vector store. You can start this vector store anytime because it goes to its own bank, right? Own port, not own bank. Clearly, different elements in this vector store go to consecutive banks, as we have discussed. So basically, you can parallelize almost completely any number of loads as long as you have 1 port servicing it, and stores also. So this brings us to 79 cycles. And this is, if you compare it to 1504, that's 19x performance improvement, which is not bad. You could say that, okay, this is maybe unfair comparison. We beefed up the memory system, yes. But you could also say that the in-order processor was not going to utilize that memory system anyway, because it's not capable of doing so. Out-of-order processor, maybe. You need a bigger instruction window, but in-order processor, give this memory system to the in-order processor, it's not going to do much. It's going to do a little bit by the first 2 loads, actually, but not that much. Does that make sense? Okay. Okay, so this is the advantage of vector processors, as you can see. Large performance improvements and large efficiency improvements. Now let's tackle some questions that make programming a bit more harder also. So what if number of data elements are greater than number of elements in a vector register? This is relatively easy. You need to break the loop such that each iteration operates on number of elements in a vector register. For example, if you have 512 data elements that you're operating on for some reason, and you have 64 element vector registers, you basically need to have a loop of the code that we kind of showed. You need to have 8 iterations where vector length is 64, and you need to have 1 iteration where vector length is 15. Now, the downside is these 8 iterations where vector length is 64 is nice because you don't need to change the vector length. But when you change the vector length, a lot of things in the machine changes, right? You were assuming some vector length and you change the vector length. You need to actually wait a lot. It introduces a lot of stalling. I'll let you think about that. But this is called vector strip mining, and it's actually coming from the mining terminology. You have some really interesting part of the mine, gold. To reach the gold, you got to get rid of the chaff, right? So you basically strip mine the top of the mountain, and then you reach the gold. What is gold? Gold is 8 iterations where vector length is perfect. The rest is dust or whatever you're strip mining, right? And if you read this, basically, you remove the soil and rock overlying the mineral deposit, which is the gold. Okay, people are very inventive, as you can see, right? Okay, so now let's talk about some more thorny issues. What if vector data is not stored in a strided fashion in memory? What if you have irregular memory access to a vector? Basically, the idea is to use injection. Remember the load indirect that we introduced in LC3? It's going to come back to us right now. We're going to do inject loads. So we're going to use injection to combine or pack elements into vector registers. These are called scatter-gather operations. They're very popular today because of sparse matrices especially, which is used in machine learning quite a bit. Basically, yeah, this says that. Doing this also helps with avoiding useless computation on sparse vectors. Basically, instead of, if you have a vector, you have 1 billion elements, only 3 of them are non-zero. It doesn't make sense to go through all billion elements and do operations on 1 billion elements, right? Assuming that 0 doesn't contribute to your computation, which is not the case in most cases. Multiplication, for example, 0 is useless, right? You gather only those 3 elements, pack them into a vector register, and operate only on those 3 elements. That's the idea, basically. And then you scatter them back to memory where they were supposed to be. That's the idea, basically. So this could be extremely advantageous in those situations, as you can see, right? But it's not the only case where it could be advantageous, as we will see. I'm going to actually show you another example, which is these inject accesses. So let's assume that you want to vectorize this loop. Somebody gave you this loop, and somebody asked you, is this vectorizable? Your answer should be yes. Why? Because loop iterations are independent of each other. Clearly, there's an injection over here that makes things a little bit more complicated, so we need to do something about it, which we did not do before. But whether or not this is vectorizable is not questionable, it is vectorizable. So basically, we're going to introduce this index load instruction. What we will do is, so D vector, this D vector is essentially we load the indices into this D vector, yeah. And then we do a load indirect from RC based. What this instruction will do is, so here you have a vector of indices that are specified by D, and then we do a load indirect where you take RC and add the index to it, and for each element of each vector, of this vector, and then load it into consecutive elements of vector C over here, okay? And then you can actually do the rest. The rest is easier, of course. The rest is what we have seen. This is the different part, basically. You need to load the indices, and then you do a load inject. Now let's take a look at an example. Essentially, these are often implemented in hardware to handle these sparse vectors, as I mentioned, or indirect indexing. Vector loads and stores use an index vector, which is added to the base register to generate the addresses. Let's take a look at an example of a scatter, not gather. So this is our index vector. These are the locations from a base address that we're going to store this data vector to. Now, this is a simple example. We have only 4 elements, but what this means is that the vector should be stored this way in memory. At base location, which needs to be specified somewhere, +0, we should store 3.14. At base +2, we should store 6.5. At base +6, we should store 71.2. At base +7, we should store 2.71. And the rest we don't touch. Okay? So basically, this is a vector. This is a vector. You just need to do store base plus, basically the operation is a vector store. And this vector store takes a base address and adds it to the element of the index vector, calculates the address, and stores the data over there. Basically, you're scattering the data using this vector scatter store operation. That makes sense, hopefully, right? Okay, gather is very similar, except you do the opposite. You can actually use the same example to gather from memory. You don't have this data vector. You're going to populate the data vector. You give it an index vector, and you do a load using the base addresses. Each consecutive element adds the base address, each consecutive operation adds the base address to these different indices, and you load from these different indices into the data vector. Okay, you can convince yourself that this is relatively easy. And clearly, this example doesn't do justice to it because it's an 8-element. We show 8 elements, and 4 of them we don't care. But whenever you look at an example like this, think about the example I provided. You have 1 billion elements. Only 3 of them are really numbers that you operate on, non-zeros, let's say. Okay, let's talk about some other things, conditional operations. We've already talked about this actually, but I just want to give you an example. What if some operations should not be executed on a vector based on a dynamically determined condition? Like this sort of, again, if somebody asks you, is this vectorizable? You will say absolutely yes, because loop iterations are independent of each other. But there's some conditional flow execution. If an element is not 0, then you store the result of this multiplication into the destination B vector, as you can see. If an element is 0 of AI, then you don't actually do the store. So basically, the idea is to use masked operations. You set the vector mask register. It's a bit mask determining which data elements should not be acted upon. So this is how you would translate this code. You vector load V0, V1, A, and B, as we normally do. And then we set the vector mask register by checking whether each element of vector 0 is not equal to 0, as you can see, based on this condition. This sets the vector mask register. Elements corresponding to not equal to 0 being true are set to 1. And this vector everything after this takes into effect depending on this vector mask. So for example, when you do this vector multiply, you do this multiplication, but only the elements for which the mask bit is set actually updates the corresponding elements. Makes sense, right? The multiply takes effects only for elements for which the mask bit is set, basically. For all of those elements where the mask bit is not set, the multiply doesn't take effect. So this is conditional execution. That's true for store also, actually. So in order to be able to go back to unconditional execution, you need to reset the vector mask register to all ones. So if your vector mask register is all zeros, these are actually no ops, right? Makes sense, right? You still execute them, but in effect, they're no ops because all of the elements in the vector mask register are zeros. So this is actually predicate execution. We did not cover predicate execution much when we talked about branch prediction, but essentially this is converting a branch instruction into data flow, right? That vector mask is providing conditions, and those conditions decide whether an operation takes effect on an element. There's no branch. It's all data flow, right? It's all dependent on the vector mask register. So this is beautiful, and this is where predicate execution has been extremely successful. Execution is really predicated on the mask bit. If the mask bit is 1, but actually it applies to all operations in a vector processor. I did not talk about this, but here the vector mask is all ones. That's why all of these are unconditional. But once you change the vector mask and vector mask changes a little bit, if some element has a corresponding element in the vector mask that's 0, then that doesn't take into effect. Okay, so this is another example with masking. This is actually more sophisticated, but I won't give you the code. You can write the code. And this is again vectorizable. But now we're checking if AI is greater than BI. If that's the case, we set CI to be AI. Otherwise, we set CI to be BI. What we need to do is we need to compare A and B to get the V mask. And then we do a mask store of A into C. And then we complement V mask, that's else. And then we do a mask store of B into C. And then once you go out of this loop, let's say, you set the V mask to all ones. And this is what you do. So you can actually do operations on the mask vector also. So basically, you're doing predicate computation on the mask vector. This is very powerful. In fact, ARM ISA had conditional execution a la these processors, but then they got rid of it because it was very difficult in a scalar processor. But in a vector processor, it makes a lot of sense because it gets rid of these branch instructions completely. Okay, so basically, this is the execution. If this is your A vector and B vector, this is what your V mask will be. And you can, again, convince yourself by comparing AI greater than or equal to BI. So how do you implement these mask vector instructions? A simple implementation would be execute all of the operations, but turn off result write back according to the mask. So these are the mask bits, elements corresponding to the elements going into the functional units. So let's assume that there's a multiplication. You do all of the multiplications, but before you write the elements into the vector register, you check whether the mask is 0 or 1. If it's 0, you don't write the element to the vector register element entry. If it's 1, you do. Now, this may be very energy inefficient, as you can see, because if your vector mask is 0 for almost all the elements, you're doing lots of computation in your functional units, but you're not writing back the result. So another implementation is this density time implementation, where you first scan the mask vector, and you figure out which ones are actually ones, and only execute those operations in the vector that are ones. That's the idea. Which one is better? It depends on basically the complexity of the scanning and also how many zeros you have in the mask. Okay, so I'll let you think about that. So there are some other issues. So stride and bank count, let's revisit this. So actually we've assumed stride 1, but as long as the stride and bank count are relatively prime to each other, such that they're not divisible with each other, and there are enough banks to cover the bank access latency, you can sustain 1 element per cycle throughput. This is the real generalization. You need your stride and bank count to be relatively prime. How do you make sure that happens? Good luck. Especially if you have a 2 to the power of 2 number of banks, 2 to the power of n number of banks, this is very difficult to achieve. If your banks can be a prime number, well, that becomes interesting now, but then how do you do the address mapping with a prime number? Okay, so basically, we talked about the row major, column major. I'm not going to talk about this. I want to talk about a few more things before we finish. You can leave if you need to leave, but I'm almost done. So basically, you need to change the stride when accessing a row versus column. And we've already seen this. Basically, this is very difficult to achieve. The purpose of the initial example was very difficult to achieve. different strides can lead to bank conflict. This is a stride of 1, this is a stride of 10. But now when you start doing something else, when you start multiplying this vector with this array with some other array, then you may actually start getting bank conflicts. So basically, how do we minimize them has actually concerned vector processor designers a lot. And a lot of what has been implemented in vector processors trickled into our systems today. Because we need actually to minimize bank conflicts. More banks. We have more banks today. Expensive. More ports in each bank. Expensive. Better data layout to match the access pattern. How do you do that? You need a hero programmer for that. Is this always possible? Maybe not. Better mapping of address to bank. Now this becomes interesting. People have actually proposed a lot of mathematical randomized address mapping schemes. You take an address and memory controller randomizes the address mapping in a predictable function, of course, such that the probability of conflict reduces as much as possible. And this is a beautiful paper that talks about the idea. You may recall the name Bob Rao. This is the person who developed the VLIW processors also, but he had actually worked a lot on vector processors in the past. And you can see that there are a lot of mathematical theory that goes into randomizing the address mapping function to banks. Which address should go to which bank, basically. We're going to get back to this in memory system. So let me, shall we take a couple more minutes? I think we're already a couple more minutes more. Who says we should take a couple more minutes to finish this part? Otherwise, okay, some people, who says I want to go? If you want to go, you can go. No problem with that. Okay, let me finish since more people raise their hands. This is interesting because this is going to finally put things together. So array versus vector processor is really a distinction, a purist distinction. Most modern processors are actually a combination of both. They exploit data parallelism in both time and space. Now let's take a look at this. And one of the reasons is array processors are actually too idealistic, right? If your vector length is 1,000, it's very difficult to get 1,000 processing elements. Well, today you can actually, let's say 1,000,000. 1,000,000 of vector length, 1,000,000 processing elements that do everything. That's very difficult to get. So in the end, you really need to pipeline like a vector processor does. So let's take a look at this instruction. Vector add ABC. So this is a vector execution, right? Consecutive elements go to the same functional unit in consecutive cycles. That's time. Now, this is what really happens in existing systems. You have some number of functional units that can execute the same function, and you feed some elements in parallel, as you can see, the first 4 elements in parallel, but then you pipeline the remaining ones in parallel across these functional units. So you can see that you're exploiting both space, a parallelism in both space and time. That sounds good. Now you can also customize the register file. Registers that are numbered, or elements that are numbered 0, 4, 8, 12, 16, 20, 24, go to this one. The other ones go here. Basically, there's a function, there's a mapping, there's a partitioning of the register file across these functional units now. Not all registers need to feed all functional units. This makes it a little bit more harder to program also, actually, later. So basically, this is what a GPU kind of looks like today. You have a partitioned vector registers, as you can see, and you have what's called a lane. A lane is essentially functional units that operate on a piece of the register file. And you can actually have multiple functional units, as you can see over here. Okay? So, well, you can also think of this as a functional unit that is like an array processor, array functional unit. But then there's a lane in each one. And you actually pipeline the results in each one, but then you also exploit the space parallelism. So let's take a look at an example over here. You can overlap the execution of multiple vector instructions. We have an example machine over here that has 32 elements per vector register and 8 lanes. And we're going to look at how you do the load units. So 8 lanes. In the first cycle, you send 8 elements. In the next cycle, the next 8 elements. In the next cycle, the next one. And then you can start to multiply concurrently, and then you can start the add in the next cycle, basically. So if you look at this, the instruction level parallelism you get in the steady state is 24 operations per cycle, while you issue 1 vector instruction per cycle. So this is quite good, if you will. Okay. I'll do this also very quickly. As I said, you can automatically vectorize code. This is a perfectly vectorizable loop. If you look at the scalar code, this is what you do. You load the first element from A, you load from B, you add them up, you store into C. This is the iteration, first iteration. I'm ignoring the branch over here. This is the second iteration. Now, automatic vectorization, or if you're vectorizing your program, you realize that these are independent, and you put the loads across different iterations together. That's what we're really doing, actually. This is scalar code, but you can take scalar code, do the dependency analysis, and put the loads together and vectorize them. So this is a vector load. This is another vector load, a vector add, a vector store. You're really fusing iterations when you think scalar. When you think vector, you don't even start with scalar, of course, right? That's the idea. So vectorization is really a compile time reordering of this operation sequencing, but this requires extensive loop dependency analysis to make sure that different iterations are independent of each other. So let me summarize. Basically, vector and SIMD machines are really good at exploiting regular data parallelism. You perform the same operation on many data elements. This improves performance, simplifies design, improves energy efficiency, but performance improvement is limited by vectorizability of code, and scalar operations limit vector machine performance. And always remember Amdahl's law, 99.9%. And Cray1 was the fastest scalar machine of its time. Scalar was written in capitals for a reason. So many existing ISAs actually were influenced by vector machines. They started including these SIMD operations. That's what we're going to talk about next in the next lecture. And then GPUs are clearly modern vector plus array machines that actually have a different programming paradigm. And we're going to talk about that. But these have been there before GPUs became popular, let's say. But these are actually vector instructions in a limited way. Okay. So this is where Today we're going to talk about GPU architectures. Everything is fine online? Okay. GPU architectures. We're going to build on SIMD processing that we covered last time. And clearly, this is a fascinating topic. GPUs are parallel computers that you have in your pocket that nobody had the luxury to have in the past. People used to build supercomputers that are much, much, much less powerful than today's GPUs. Today, you have it in your pocket. So you can imagine the computational power we have today. It's fun to learn about GPUs. But I'm going to first remind you about what we covered, SIMD processing. And then we're going to talk about SIMD operations in scalar ISAs or von Neumann architectures. So von Neumann architectures actually incorporate SIMD operations as well, as we will see. And then we're going to jump into GPUs. So you can see the impact of SIMD processing everywhere in our lives. Okay, these are some readings. And this is where we will start. Remember, SIMD processing is all about single instruction, multiple data. We're exploiting regular data level parallelism. And we discussed the seminal paper that divided the computing spectrum paradigms in terms of the instructions and the data on different axes. And single instruction operating on multiple data elements falls into SIMD. And we discussed two types of pure SIMD processors, array processors and vector processors. And I mentioned in last lecture that existing GPUs combine both of these types. So this is really a purest distinction today. Existing GPUs are both array processors and vector processors. If you get the trick question in an interview, for example, so if someone asks you, is GPU a vector processor? You say yes. Is GPU an array processor? Yes. Except it's programmed in a completely different way, as we will see today compared to traditional SIMD. And just to jog your memory, what's an array processor? What's a vector processor? Essentially, these both have multiple processing elements, and they can execute multiple instructions at a given time. Except array processor has much more powerful processing elements where each processing element can do any operation. And this way, you can actually execute the same operation at the same time on all processing elements on different data elements, different data inputs. You can see that at a given time, all the processing elements are executing loads in the first cycle, adds in the next cycle, multiplies in the next cycle, and stores in the next cycle. Vector processor is more frugal, meaning the processing element can be simple. As we discussed, you can have different processing elements specialized, load unit, add unit, multiply unit, store unit, for example. Each unit doesn't have to do everything. And that's why it's actually easier to build. But here, you cannot execute the same operation on multiple processing elements at the same time. You have to pipeline it over time. But if you look at space, you basically execute one operation in the same space, but different operations in the same time. That's how you exploit the parallelism, basically. And in real processors, we combine both of them. And we said that SIMD is very powerful because it enables a single instruction to specify huge amounts of work, because you're doing the same operation that's specified by the instruction on many, many elements, billions of elements potentially, right? Maybe you can turn off the admitting over here. I don't know why Zoom has this. Yep, I can hear myself here also. Okay, yeah. Basically, this is a bad design in software, as you can see, right? The software should not really interrupt the presenter. Why should the presenter be admitting some person over there, as you can see, right? Okay, so there are design principles you can see, and this is broken in this piece of software, if you will. Okay, so basically, you can see that vector processors are more frugal, but both of them really execute a lot of operations. Okay, well, what was I saying? Basically, a single operation specifies a lot of work. This way, you don't need to decode, fetch the same instruction many, many times, right? I mean, you've seen that. But because of the same reason, a single operation specifies a lot of work on a lot of amounts of data, a large amounts of data. We need a more powerful memory system. And the remaining 6 lectures, we're going to talk about the memory system. And 6 lectures are really not enough to talk about the memory system, as we will see. This is really the most important part of today's machines. And a GPU has a very sophisticated memory system. And we talked about vector processor memory system. Basically, we said that you need to be able to sustain n concurrent accesses if you actually want n elements at a time. In an array processor, you need n elements at a time if you're doing a array load, right? Vector load on an array processor. And we will see that GPUs actually exacerbate this because they follow the same paradigm. Okay, you remember memory banking? We're going to revisit that next week, probably, maybe tomorrow. Okay, so this is how we combine the paradigms. So you have a vector addition instruction, and this is how it's executed on a vector processor. It's executed on an addition unit this way. Each, let's say, element of the vector is operated on in consecutive cycles in time. But now you can actually do both space and time in a combined array and vector processor. You can see that the first 4 elements, first 4 additions of the first 4 elements are done concurrently across different 4 add units. And then the next 4 elements are pipelined. Next 4 elements are pipelined. Next 4 elements are pipelined. So this is basically an array processor where the array width is 4, and then a vector processor also where the vector length is specified somehow by the vector register. Okay, you've seen all of this, and we've discussed that this enables us to divide the register file such that elements 0, 4, 8 come from this piece of the register file, elements 1, 5, 9, ... come from this piece. This way you can have partitioned vector registers as opposed to having a huge monolithic register file, which makes the design easier. It also clearly improves your parallelism, and this is called the vector lane. And we're going to see that a GPU is going to be very similar to this soon. I'm just going to change the terminology a little bit. So these 2 pictures, this picture and this picture, keep that in mind. You're going to see it again. In fact, this picture, you're going to see it again also. Here, the terminology is vector processing or SIMD processing. You can overlap the execution of multiple vector instructions. So in this particular case, you have 32 elements per vector registers and 8 lanes. You have 8 load units, if you will. You can do 8 loads per cycle. And how do you actually do 32 loads per cycle? You start the remaining loads in consecutive cycles. One single load operation does 8 loads in one cycle, and the vector length is 32. So it basically launches 3 more batches of 8 loads. And then you have multiply, and then you have add, and then if you have another load, it starts another 32 operations. And you can see that these are both pipelined and parallel. This way you can sustain 24 operations per cycle in this particular example. If you look at time, at a given point in time, in the steady state, you have 24 operations going on 24 different data elements. Okay, these are all review. We've seen this. We've also seen the disadvantage. We've talked about the advantages, so I'm going to focus a little bit more on disadvantages here. This works nicely if parallelism is regular, right? If you have a data parallelism or SIMD parallelism, what's called, operating on very large vectors, this is great. Unfortunately, if parallelism is irregular, you have problems. It's very hard to get efficiency out of this machine. It's a general purpose machine, so it can actually work. You can actually program it. You can actually write any program with this. But unfortunately, the efficiency is very low. Your SIMD vector length can be, let's say, 32, but you may be utilizing only 1. So you may be running scalar code on a vector processor, and that's clearly very, very inefficient, right? That's why people have built special scalar units inside the vector processor, such that those scalar instructions do not get executed on the expensive part of the processor. Okay, and I've also given you this quote from Josh Fisher on VLIW, and he's absolutely right in what he says over here. We've discussed that last time. And we've discussed that you can actually, if your program is nice, you can automatically vectorize your program. For example, if you have this loop, which is vectorizable because loop iterations are independent of each other, you can execute it like this. We're going to see this actually very soon again, in a scalar machine. Or you can identify that loop iterations are independent of each other by doing some analysis on the program using compilation techniques called loop dependence analysis. You can basically parallelize the iterations. So basically you put the iterations together, multiple iterations together, let's say vector length iterations together, and then each instruction is a vector instruction over here. This green instruction is a vector load. This brown instruction is another vector load. This pink instruction is a vector add. This yellow instruction is a vector store. And you're doing 32 iterations in parallel using vector instructions. So it's beautiful. Okay, just to summarize, we've also discussed this. This is very good at exploiting regular data parallelism. And performance improvement, unfortunately, is limited by the vectorizability of code. So I'm going to remind you of Amdahl's law again. And this is what we're going to cover next. Many existing ISAs include SIMD operations. They don't go full way of actually having a full SIMD processor inside the von Neumann machine, but they actually have instructions that operate using the same principles, as we will see. So before that, we should always remember Amdahl's law. If someone says Amdahl's law doesn't exist, you know what to say. As long as you have some sequential code, as long as your f is not 0, you're bound by, f is not 1, f is a parallelizable fraction of a program. As long as if f is not 100%, you are limited by the speed up that you're going to get. So you want to make a parallelizable fraction of a program using algorithms or different compilation techniques as high as possible. If it's not high, you know that you're dominated by this part of the speed up equation. Okay, we'll see this again very soon with GPUs. Any questions? This was a very quick overview of the last lecture. Now we're going to jump into how last lecture applies to modern processors in your pockets again. Basically, modern processors, von Neumann machines, have single instruction, multiple data extension instructions. Essentially, these are special instructions where the instruction acts on multiple pieces of data at once, as opposed to acting on two registers, register 1, register 2, one piece of data, each one element. You basically act on 4 elements at a time. Here you can see an example at the bottom from an earlier Intel multimedia extension instruction. And why were these introduced? As your suggested recommended reading describes very clearly, people wanted to accelerate graphics, multimedia, image processing applications that have been becoming more popular in the 1990s. Essentially, they did not want to change the ISA significantly or the execution model significantly. So they basically added these instructions that can perform short arithmetic operations, also called packed arithmetic. So if you look at this example, it's a packed add 8. What does that mean? Basically, you're adding 4 8-bit numbers in a packed register. Register is 32 bits itself. Each element that you're adding is 8 bits each. And you have 2 registers, as you can see. Register 0, S0, register 1, S1. And you can see that this operation's result is add the bottom 8 bits together and put the result at the bottom 8 bits of register S2, destination register. Now do the same thing for the next 8 bits for each of the registers and put the result into destination register's next 8 bits and keep doing the same thing. You can see that this is a SIMD operation, right? Single instruction operates on multiple data elements where the data elements each happen to be 8 bits. And the good news is you can modify a 32-bit ALU adder very easily, chop it up into 8-bit pieces, ignore the carry operations such that they don't actually feed into the next, let's say, 8-bit chunk. This is actually almost 0 cost, if you will, in terms of the additional hardware you add. So it's beautiful, as you can see, right? Of course, if you want to have a larger vector length, if you will, in this case, the vector length is only 4, if you will. It's not specified because it doesn't exist. Vector length doesn't exist because this is a single instruction saying this single instruction operates on 4 data elements. That's it. There's no vector length or anything, as we will see in the next slide also. But if you want to actually increase that, if you want to actually operate on 64 elements at a time, your register needs to become wider. So it looks more like a vector register at that point, right? If you want to increase, if you want to operate on 64-bit elements at a time, well, you cannot do it in this case, right? If your registers are only 32-bit wide, clearly you cannot do it. So it's limited in what you can introduce. So this was introduced first by Intel in this, as this paper describes. Basically, they called it the multimedia extension operations initially. Now it's named something else, as you will see soon. But basically, a basic idea is SIMD. One instruction operates on multiple data elements simultaneously. In this sense, it's really very much similar to array processing, right? This is not a vector processing. If somebody asks you the question, does this look like a vector processing instruction? No, it's really array processing because you're really operating on 4 elements at the same time, right? And as I said, it's designed with the multimedia operations in mind. So let's take a look at this example over here. Here we have a 64-bit register. Clearly, in a scalar operation, you can actually add 2 64-bit values by referencing 2 registers. That's a scalar operation. But there are instructions added into the instruction set architecture that can treat the 64-bit register as 2 32-bit data elements, so that you can actually add 2 32-bit data elements, or as 4 16-bit data elements, such that you can actually add 4 16-bit elements, or 8 8-bit elements, so that you can actually do 8 operations or 8 adds per cycle on 8-bit bytes, basically. So that's the idea, and it's beautiful, as you can see. There's no vector length register. The opcode is different for each of these instructions. An opcode determines the data type, whether you're operating on 8 8-bit bytes, 4 16-bit words, 2 32-bit double words in Intel terminology, and 1 64-bit quad word. And if you're doing a load, etc., stride is always equal to 1. These are basically consecutive. Okay. Does this make sense? Hopefully it's simple, right? And the operations are very similar to vector instructions. So these are the instructions that you can see. This is called packed, compare, greater than word. So basically you have 4, you chop the register into 4 words. And let's assume that this is the source register, and these are the values of the 4 words in the source register, and these are the values of the 4 words in the second source register. The result of this operation is this. Let's take a look at the ISA definition. Compares packed 8 bytes. Well, in this case, I think 4 16-bit words. Result is mask of 1s if true or 0s if false. So you basically compare 51 to 73. 51 is not greater than 73, so the result is all 0s in these 16 bits. 3 is greater than 2, so the result is all 1s in these 16 bits. 5 is greater than 5. No, that's not true, so the result is all 0s. 23 is greater than 6, so the result is all 1s. So now what you're seeing here is you're creating a mask. Remember the vector mask register? We had that as a special register in a SIMD processor. Well, we have it in a general purpose register over here. The destination register specifies the mask. And we're going to use that as a data element to actually decide which operations take effect or not by programming this in a nice way. Does that sound good? Okay, so you can see there are many, many operations. These are actually more advanced. At the time, this is 1990s. They basically add the packed, multiply, add, word to double word. So basically you have a very similar view of the same register, 4 16-bit words, another 4 16-bit words. What this instruction does is, it basically does this operation. It's multiply and add. It multiplies the corresponding 16-bit words. A0 times B0 goes over here. A times B1 goes over here. A2 times B2 goes over here. A3 times B3 goes over here. And then it adds the top parts. Basically, this is the addition, and this is the addition. Why? You can actually do a matrix vector multiplication using these operations, as we will see in the bottom part. So you can see that you can actually do matrix multiplications. And this is how they describe how to do it. I will not go into this in detail, but you need to do these operations. This is called the packed, multiply, and add, word to double word. Unfortunately, the instructions are very ugly, as you can see, but they make sense. You basically do this multiplication addition, and then you do another packed add so that you can actually reduce the adds so that you can do the matrix vector multiply. If you're interested, you can read the paper for more, but it's not magic. It's all doable with instructions, as you can see. Okay, let me give you another example. This is the image processing example that they provide in this nice paper. Unfortunately, they don't have colorful images in this paper, so we tried to add a little bit of color. Basically, these are the types of operations they were targeting. Essentially, you have this image X, let's say, and then you have a background image Y, and there's a blue background in image X. Now, the idea is to replace that blue background, doing some image processing, with some blossom background. It looks like a tree over here, and then obtain this image. So this is standard image processing, very, very simple operations, if you will, by today's standards. But if you don't have parallel operations, it's actually slow. So this is the loop that you would write to do this. You go through every pixel in the image. You check if the source pixel is blue. If it's blue, in the new image, you replace it with a pixel coming from this second image. That's the idea. Otherwise, new image stays the same as the original image, right? That way, you will have this lady behind a nicer background of trees as opposed to a blue background. Okay. So how do you do this with scalar operations? Basically, this becomes all scalar. It becomes all scalar. But with MMX, multimedia extensions, you can operate on 8 pixels at a time, essentially, assuming each pixel is 8 bits. And you can see this nice instruction that we saw earlier, packed, compare, equal, byte. Basically, you load 8 pixels of this image in MM1. That's the register name. Assume that all of them are blue over here. Nice. And then you basically, this is MM1. This is basically you're comparing everything, whether it's blue or not. This is basically the thing that you're going to try to mask with. And then you load 8 pixels of this image into MM3. And some of them are blue and some of them are not blue, as you can see. These are coded. And what this instruction does, it compares whether the value over here is equal to this value or not. So, and then the result is a bit mask. So if these two 8 bits are equal, you'll get ones over here. In this case, they're not equal because this is blue and this is not blue. It's encoded some way, of course. These are zeros. So these 2 pixels over here are not blue, so you get zeros in the bit mask. These 2 pixels happen to be blue, so you get all ones in the bit mask. And these 2 pixels are blue, you get zeros, and these are not blue, and you get zeros, and these 2 pixels are blue, and then you get ones, as you can see. Okay, so how do you take advantage of that bit mask now? Basically, remember what we were going to do is we were going to take the blossom image and replace the original image when original image actually matches the blue parts. So if the bit mask is 1, in the final image, we should actually, the pixel should come from the blossom image. If the bit mask is 0, in the final image, the pixel should come from the original image. Makes sense, hopefully, right? And this is what these instructions essentially do. Basically, you take the blossom image, 8 pixels at a time again, and then you end it with the mask, and then you get a result. And this is a partial image that contains the pixels that are blossom, as you can see. Everything else is zeros. And then you take the original image and end it with the mask. And not with the mask, because basically you need to pass the pixels from the original image, which are marked in red over here. So if the mask is 1, the result is 0. If the mask is 0, you pass the original image pixels. That's why this is and not. Okay, and then you basically OR these 2 things. And hopefully, because of the way we have constructed the program, in the final image over here, or final 8 pixels of the image, you have the blossom image in places that were blue in the original image, and you have the original image in places that were not blue in the original image. That's the idea, okay? So you can do this essentially with this instruction sequence. These are loading 8 pixels from the original image and then the blossom image to 2 registers. And then you do the pack compare equal, which sets the mask in MM1. And then you do the packed end to get the blossom image in appropriate locations. And then you get the packed end not to get the original image in appropriate locations. And you OR them into registers so that you can actually construct the final 8 pixels on the image. And then, of course, you need to iterate. If the image has 1,000,000 pixels, you have to go through all of them 8 at a time, right? But you can parallelize it right now. Before, you were going through 1 element at a time. Now you're going through 8 elements at a time. So hopefully you can speed this up by close to 8x, right? Assuming it's perfectly vectorizable. Well, it is perfectly vectorizable, but then there's some serial code that you may need to deal with clearly, right? Does that sound good? So it's beautiful, as you can see. It's not magic, but it's very similar to what we have done earlier, except we didn't deal with vector length, because vector length is encoded in each instruction. And we dealt with vector mask in a very different way, right? Vector mask is really a general purpose register over here, and we use it as part of the operands to the instruction. Okay, you can read this paper, but basically they say that MX speed up computation intensive inner loops or subroutines on average between 3 to 5 times. And they give some examples. For example, an MPEG-1 video decoding application at the time. Today we're actually much further. We are beyond MPEG actually in many cases. On a Pentium class processor with MX technology executes 1.5 times faster than the same application on the same processor, not using the MX technology. And then you can see that Intel plans to implement MX technology on future Pentium and Intel architecture processors, blah, blah. And they believe that it will scale well with CPU operating frequency and future Intel microarchitecture generations. So you can see that these folks actually were prudent to write this paper at the time, right around the time they were actually releasing it. So it's good that people are doing this. In fact, if you know the backstory at Intel, this was actually a very controversial thing to put out, because they said, we're changing the ISA significantly. Who's going to use these operations? And then the people who are, let's say, more progressive won. They said, release it, and there will be a lot of people, because this is actually used in many systems. And clearly, they did the right decision at the time. So this is always a decision, right? You put something into hardware, will people use it? A lot of companies worry about that. If you actually have good evidence that there are a lot of applications that may potentially use it, then go for it, right? And today, actually, people don't use it just for graphics. We do a lot of research in bioinformatics, for example. There's a lot of parallelism that you do when you compare different genomes. You basically can use all of those operations very nicely when you compare different elements. Text comparisons, for example, clearly machine learning also. So these extensions have improved a lot over time. I will not go through this, and you don't need to clearly know all of this, but initially, you had 64-bit MX registers. Over time, Intel changed their names, like streaming SIMD extensions for marketing purposes, etc. Basically, they added a lot of new instructions, like shuffle operations and double precision floating point operations, larger registers so that you can exploit parallelism. AVX extensions are also the older version right now. Now you could operate on 512-bit things. Now, 512 bits is, if you're operating on 8-bit values, that's 512 divided by 8, right? That's 64 elements at a time. If you're operating on 64-bit values, still 8 elements at a time. Not bad, right? But of course, think about 512 bits now. Your memory system needs to support all of that as well. And more recently, Intel introduced these advanced matrix extensions like everybody has been introducing, right? Here you have 2-dimensional registers and a tiled matrix multiply unit, and you can read about it also. Basically, this supports matrix multiplication. And we're going to see that GPUs also introduce these specialized units soon, even though they're SIMD machines. Okay, any questions? We're still talking about extensions, not GPUs yet. But let me give you an idea of SIMD operations and their popularity. Other machine learning accelerators take advantage of SIMD operations as well. We've talked about Cerebras' wafer scale engine. I'm going to very quickly go over a very brief overview just to show you that this actually takes advantage of multiple paradigms. So they have this number of cores, and they map a neural network onto a whole wafer. And basically, they have many processors to map things onto. So you cannot see all the processors over here, but it's literally multiple instructions operate on multiple data elements. It's a multiprocessor is multiple instruction, multiple data machine, as we may see later on also again. But you're operating, you have basically different programs running on different processors. But if you look at each processor, so this is basically this is the MIMD machine. It's actually very interesting. It incorporates some concepts that are more advanced for this course, but for future courses, we cover a lot of these. Basically, you connect many processors using a 2-dimensional mesh interconnection fabric such that they actually communicate with each other. But each processor looks like this. You can see that there's a floating point multiply and accumulate unit. And you guessed it's a SIMD unit. Basically, each of these have some memories, and they communicate with each other. But each of these processors is a SIMD processor, actually. It has 4-way SIMD for 16-bit floating point operands. Not very powerful. You can do 4 floating point operations per cycle. And it has a local memory as well. And you can do floating point multiply and accumulate. And the basic idea is you map your neural network computations to these floating point multiply and accumulate operations. Very similarly how we did with systolic arrays, except this is a SIMD machine right now. Remember that picture that I showed you when we talked about systolic arrays. You can convert a convolution to a matrix multiplication. Essentially, that's what they're doing. They're converting convolutions to matrix multiplications and doing them using these four wide vector operations or SIMD operations. Okay, if you're interested, there's a lot more out there that talks about this. But I wanted to point out that SIMD operations exist in machine learning accelerators, specialized for machine learning as well. Now let's jump into GPUs. How many people have programmed GPUs here? Okay. I think I asked this question somewhat before. Not many. Hopefully you'll program them. It's fun. They need to be a bit better programmable. But basically, GPUs are SIMD engines underneath. What we've discussed apply to GPUs. I'm going to show you how it's different in GPUs. The instruction pipeline operates like a SIMD pipeline. In other words, like an array processor, as we will see. However, the programming model is completely different. It's not done using threads. It's not done using SIMD instructions. It's done using threads, and we're going to see this in a little bit. So let's go back to our parallelizable code example, which I really like. But before going to that, let's distinguish between different things. Programming model in software versus the execution model in hardware. So these two things are very different things. And we've seen examples of this, right? You can have a von Neumann-based scalar ISA programming model, sequential code, and it can execute it data parallel, right? We converted the von Neumann program to a SIMD program in the earlier lecture. Data flow, we've discussed this. And multi-threaded, you break things into threads. How many people have done multi-threaded programming here? Okay, I expect more people. That's good. So multi-threading, you break the program into tasks, basically, and parallelize them on multiple processors or multiple threads, hardware contexts. Now, execution model refers to how the underlying hardware executes the code underneath. It doesn't have to do anything with the programming model. Of course, if it matches the programming model, that's better, right? Because you can exploit the type of parallelism expressed by the programmer. But it doesn't have to. So, for example, you can have out-of-order execution, like we have seen, vector processing, array processing, data flow processing, multiprocessors, multi-thread processor, etc. An execution model can be very different from the programming model. For example, von Neumann model is implemented by out-of-order processors today. Underneath, the execution model is not sequential, well, strictly, right? Underneath it's data flow, as we've discussed, except because you have to obey the contract, you have to eventually give things back sequentially to the software, as we have discussed, right? A GPU is somewhat similar. It implements some model. Programming model is called SPMD, as we will discuss, single program, multiple data. It's a version of multiple instruction, multiple data programming. But it implements, GPU actually executes this code on a SIMD processor, single instruction, multiple data. Now, this may sound like magic, but basically, GPU takes advantage of the fact that there are many threads executing at the same instruction. And it gathers them together somehow. Because the programming model first expresses it nicely, as we will see. And even if the programming model doesn't express it, GPU can actually gather many threads together that are executing the same instruction and put them into the pipeline. Okay, so let's take a look at these examples. This is our code, very simple, vectorizable. And this is the scalar sequential code. This is how you might program it, right? I don't show the instructions, but you can imagine what the instructions are, and we don't have the branches clearly over here. So let's examine 3 programming options to exploit instruction level parallelism in this sequential code. Sequential, single instruction, single data, data parallel, single instruction, multiple data, and multi-threaded, multiple instruction, multiple data, or SPMD, as we will see. Now, sequential looks essentially like this. There's a branch also, etc. This can be executed. Hopefully, you can write the code, sequential code, MIPS code, for example, for this. This can be executed in a pipeline processor, right? It exploits some instructional parallelism. We've seen that. This can be executed in an out-of-order execution processor. What out-of-order execution processor does is it can find out that these 2 loads are independent, right? It can execute them together. It can also find out that this add is independent of anything else over here. that can execute that. So out-of-order execution, by looking down in the instruction window, it can find that all the independent operations, theoretically, basic independent instructions are executed when they're ready. And the big benefit of out-of-order execution in this piece of code, this kind of code, is different iterations that are completely independent of each other. We know that. Out-of-order execution does a lot of work to find that out. It doesn't even find that out, right? It just finds out which instruction can be executed when. That's it. But the end effect is that it can take all of these different iterations in the instruction window and it can execute them in parallel in multiple functional units. So it's really parallelizing. It's really taking advantage of the fact that these different iterations are parallel. And also, even within an iteration, there's parallelism between instructions. So in other words, the loop is dynamically unrolled by hardware. If you have heard of the term loop unrolling, you basically unroll the loops. You don't need to know that, but essentially, dynamically, the hardware is unrolling the loops, iteration by iteration. Okay, a superscalar or VLIW processor, which we have seen also, goes to the next step, right? It's orthogonal to out of order, actually. Both of these concepts are orthogonal to out of order. But basically, you can fetch an instruction, multiple instructions per cycle. Right? Same iteration, different iterations, doesn't matter. You could do that, okay? So you can using the scalar sequential code, we've seen a lot of paradigms to accelerate it. VLIW, of course, does the compile time analysis to figure out which ones can be executed in parallel and packs them together, and then executes different operations in parallel in a given cycle. So that's good. And we've seen all of these paradigms. Let's take a look at SIMD. We've also seen SIMD. We know that these sequential, these iterations are independent of each other. So we can actually vectorize them or create SIMD instructions. So you put a bunch of iterations limited by the vector length in the end. Either the programmer or compiler generates a SIMD instruction to execute the same instruction from all iterations across different data. Basically, this is a SIMD instruction, right? You realize instructions, iterations are independent. These loads can be executed in parallel, and only a single load instruction can express a vector instruction. So vectorized code looks like this. This is a vector load. A goes to V1. Of course, you need to have a vector length specified, right? But we are assuming that n is large, so you can actually have a huge vector length, if you will. And then the next load is another vector load. B goes to V2, vector register 2. The next instruction, vector instruction is a vector add. You add V1 and V2, the result goes to V3. The next instruction is a vector store. V3 goes to C. It's beautiful. What we have just done is automatic code vectorization, basically. The compiler needs to do the hard work to actually make it happen, but the compiler can do it in this easy piece of code because you can see that there is no dependence across iterations, right? This is a very easy to analyze code. So this is best executed by a SIMD processor, a vector and array, and we've seen that. We've seen that you actually have only 4 instructions over here. Beautiful. Now, the same code, you can execute it as multi-threaded. Basically, each iteration is independent again. We're going to take advantage of that. And we're going to say different iterations are executed by different threads, right? Programmer or compiler generates a thread to execute each iteration. Each thread does the same thing in this particular case, right? But on different data. But sounds good. You can execute this in a multiprocessor also, right? You can basically say each iteration goes to a different core. And all of the cores execute. And of course, you need to have some, in the end, something to make sure that everything is done. So this can be executed in a multiprocessor nicely. And if you have 1 million iterations, 1 million of them can go to 1 million different cores. Sounds good. And cores can be very simple potentially, right? That's the beauty of potential multi-processors. Now, we're going to also realize that there's a special aspect of this particular model. Here, each iteration does exactly the same thing. Meaning each thread does exactly the same thing on different data elements. Exactly the same thing, meaning that they have exactly the same code. This doesn't mean that they execute exactly the same operations, clearly, but they execute the exact same code. There may be branches, so they may actually change what they execute. We will see that. That will complicate things. But because each thread has the same code, this is also called a single program, multiple data paradigm. You have a single program, you replicate it, and each of them operates on multiple different data elements. And it can be executed on a SIMD machine. And that's what a GPU is basically. A GPU is programmed using the single program, multiple data paradigm. And a GPU acts like a SIMD machine. Whenever it realizes that these threads are actually executing the same load, it combines them. Okay, so this is also called single instruction multiple thread in NVIDIA terminology. Not a bad terminology, I think. Basically, single instruction comes from multiple threads at a given time. So basically, a GPU is a SIMD or SIMT machine, except it's not programmed using SIMD instructions like we did yesterday. It's programmed using threads that everyone is familiar with. SIMD is a bit harder, if you will. But the threads need to obey this SPMD programming model. Each thread executes the same code, but operates on a different piece of data. Now, this looks very nice for graphics, right? Remember the image? We're doing the same operation, same set of operations on many, many elements of data, right? That's why this fits nicely. Each thread has its own context. It can be treated, restarted, executed independently. That's a benefit over here. It's more flexible than a SIMD machine. In a SIMD machine, it's very hard to change the vector length, for example, easily. So a set of threads executing the same instruction are dynamically grouped into what is called a warp. This is NVIDIA terminology. Wavefront is the AMD terminology. I'm going to describe this in a little bit. But basically, the hardware groups these threads that are executing the same instruction, meaning that are at the same program counter. Of course, initially, this is easy if your programming model expresses this, right? And it does. But you can do more. So a warp is essentially a SIMD operation formed by hardware, as we will see. So let's take a look at this. So let me define warp. Warp is a set of threads that execute the same instruction, i.e. at the same program counter. So this is warp 0 at PCX, assuming the program counter of this load is X, right? Because these different threads are executing the same code. They're both at program counter X. They're fetching the code from the same location in memory base. And this is warp 0 that goes to the next instruction, PCX plus 1. This is warp 0 that goes to the next instruction, PCX plus 2. And warp 0, PCX plus 3, okay? So basically, you can treat these different threads that are executing the same operation as a set of warps that execute the same operation. Okay, we're going to see how that is executed soon. So basically, graphics processing units are SIMD that are not exposed to the programmer, if you will. Threads are exposed to the programmer, but underlying, we do something else. So let me discuss this a little bit more. What is SIMD? SIMD, what we have done last week, we have a sequential instruction stream. Actually, we did it a few minutes ago also. We have a sequential instruction stream of SIMD instructions. Vector load, vector add, vector store, right? We've seen that earlier. Each instruction specifies multiple data inputs. You need these instructions, and you need a vector length. I'm ignoring the vector mask for now. We're going to treat that interestingly soon. Whereas SIMT is multiple instruction streams, multiple threads, in other words, of scalar instructions. So what you do is really sequential scalar programming. You don't need to think about a vector length. You just say, this is the code I want to execute on a single element. And if I happen to execute this code on 1,000,000 elements, that's great. I'll specify the size of that block and execute this code on that 1,000,000 elements. I don't need to deal with vector length. I don't need to deal with vector mask. GPU will do that automatically. Okay. So basically, this is what we do. These are scalar operations. I don't care about vectors. Load, add, store, just like I program a sequential von Neumann machine. And I say number of threads. Well, we will see number of blocks, actually. So there's a little bit more over here, but it's the same thing. So what are the advantages of this? So we just changed some things, but this brings about huge advantages. And this is why GPUs have been hugely successful, whereas traditional vector and SIMD processors or SIMD processors have not been that successful. Again, it's all about the programmer. What you expose to the programmer. Programmer can program in von Neumann. Let's say they're not that educated to program in something much more sophisticated. They're not that used to, in other words. Well, this is von Neumann, extend just a little bit, right? That's the idea. Hardware does the harder task. So, okay. So the two major advantages is, first, you can treat each thread separately. In other words, you can execute each thread independently on any type of scalar pipeline. You can do actually multiple instruction, multiple data processing. You can have a multiprocessor, and GPUs exploit that also. And you can also group threads into warps flexibly, meaning you can group threads that are supposed to truly execute the same instruction. You can dynamically obtain and maximize benefits of SIMD processing. This is actually very, very interesting, because if you find out that, okay, I have 64 threads lying out over here. They're executing, I have 20, let's say 20 threads that are lying out here. You need to keep track of this, of course. They're executing program counter X, and they're supposed to execute program counter X. And I have another 40 let's say 44 threads over here, you can combine them. And you can have a 64 thread execution to maximize the SIMD parallelism. And we're going to see that soon. So let's start with the first one. How can we treat each thread separately? Or what benefit do we get from this? You remember the notion of fine-grained multi-threading, right? We're going to go back to this. We're going to basically do fine-grained multi-threading of these threads on a very simple pipeline, scalar pipeline. So assume that we have a warp that consists of 32 threads, because somebody actually specifies that, right? If you have 32K iterations, because this is the hardware limit, there needs to be a hardware limit inside. That's not exposed to the programmer in GPUs, actually. GPU automatically breaks down a block into warps. But assume that a warp, this is what the GPU can execute in parallel. That's the vector length that's not visible to the programmer. Consists of 32 threads. Assume that we have 32,000 iterations over here in this code. And we do one iteration per thread. That means we have 1,000 warps, right? These 1,000 warps each execute 32 threads, and each of them are at the same program counter at a given point. So these warps can be interleaved on the same pipeline. So you can actually do fine-grained multi-threading of warps. I'm going to show you an example. So this is warp 0 at PCX, for example. That's the PC of the load, program counter of the load. This is iteration 0 executed by one unit over here. Iteration 1 executed by another unit. So basically you execute 32 iterations concurrently. 32 of these loads in different iterations. Now, then you may fetch warp 1 at PCX. This actually executes iteration 32, 33, ... up to 63. Fine. I'm going to show you the fine-grained multi-threading of these soon. But if someone tells you, for example, you have warp 20 at PCX plus 2, you can actually calculate which iteration it is executing, right, in the scalar code. Basically, we've divided 32K iterations. We have 1,000 warps. Each warp consists of 32 threads. Warp 20 should be at iteration 20 times 32, right? And then warp 20 should be executing the add, because we said PC at X plus 2, in iterations 20 times 32, 20 times 32 plus 31, right? So all of those 32 iterations will be executed by this warp that's executing this add. And then this warp will move to the next instruction, which is store, because each warp is executing the iteration. Okay, so let's take a look at the fine-grained multi-threading. It's the same example over here. All threads in a warp are independent of each other, so they can be executed seamlessly in a fine-grained multi-threaded pipeline. Let me give you the example. So this is warp 0. So this is a filled pipeline. Initially, you fetch warp 0. Warp 0 executes program counter X, meaning the first 31 iterations and just this load. And then next cycle, no, not next cycle actually, once it's done, it gets refreshed and it executes program counter X plus 1, because it incremented the PC, right, to the next instruction for the next for the same 32 iterations. So warp 0 is always executing iterations 0 through 31, but it gets into the pipeline once in a while so that it can execute different instructions. Does that make sense? So this warp 0 in the steady state, if you will, you can have warp 0 executing these stores at PC X plus 3 across iterations 0 through 31. In the add unit, you may actually have warp 1 at PC X plus 2 executing iterations 32 through 63. In the load unit, because you may have multiple functional units, right, you may have warp 2 executing PC X plus 1, which is load over here, but iterations 64 through 95. And then in the other load unit, which you may have again, or pipeline load unit, you may have warp 3 executing iterations 96 through 127. So you can see that different set of iterations are getting executed on different functional units. I don't even show the decode and fetch stages, but you can have something warp 4 being decoded, for example, and then warp 5 being fetched, right? Because these are doing exactly the same things. They follow through the pipeline nicely, and they're completely independent of each other. So hopefully this makes sense. So this resembles the fine-grained multi-threaded pipeline we had, right? Of course, it was scalar pipeline before, but you just extended to a vector pipeline in this particular case. Remember, each pipeline stage has an instruction from a different, completely independent thread. We've done that, right? This is the Scalar pipeline. Each of them, well, assume that this is kind of pipeline. Multiple functional units are an example of pipeline, clearly. But basically, you essentially have different instructions from different threads. And then you happen to have multiple functional units, many of them, executed concurrently in a SIMD manner. That's the idea. Okay, so hopefully that's clear. We're combining multiple concepts here, and that combination actually makes GPUs even more successful because you can have a very simple Scalar pipeline and don't do any dependence checking for branches or any other instruction because you know that the threads are independent of each other. So you take advantage of fine-grained multi-threading and you have lots of threads. Okay, so you remember the lecture on fine-grained multi-thread. So basically, to put things together, again, warp is a set of threads that execute the same instruction on different data elements. This is the SIMD, single instruction multiple thread model. All threads essentially run the same code. Why is it called a warp? Because in English, warp happens to mean this is really actually when you're actually doing manufacturing of a fabric, like weaving this shirt, for example. These are the threads that run lengthwise in a woven fabric. So they basically decided that these are the threads, and each of them execute the same thing. Basically, when you're weaving this, all of the threads are doing the same thing, right? Or you're doing the same thing while you're weaving this. That's the idea, basically. That's the analogy. That's why they call it the warp. So pictorially, this may look like this. You have a thread warp, and you have a common program counter. And a warp consists of a hardware-limited number of threads. That's a function of the hardware that you built. Each of them is scalar. And then you may actually buffer many of them. You may have thousands of them buffered, and then you feed them into a SIMD pipeline internally. In modern GPUs, you actually tens of thousands of these threads buffered, if you will. So which one do you choose to feed into the pipeline? Well, you need to make sure that the same thread doesn't go into the pipeline until it finishes one instruction in the pipeline. Basically, no two instructions from the same thread should be in the pipeline. That's the basic principle of fine-grained multi-threading, right? That ensures that our pipeline stays simple. We don't do branch prediction, dependence checking. Modern GPUs don't do any of that. No branch prediction, no dependence checking. Assuming that the code is regular and nice. If they want to actually execute more sophisticated code, they may need to do some of that going into the future. Okay, so this is the high-level view of a GPU today. It consists of a bunch of what's called shader cores. I don't know if people really use this terminology anymore, but you may hear this terminology because of the old graphics. Graphics does shading, for example, to actually do manipulation of images that you display on a graphics unit. And then there's a huge, beefy memory subsystem, which we're going to talk about next. Next week. Well, starting tomorrow. But if you look at the shader core, it's a very simple SIMD processor in the sense that you have a bunch of threads that are over here, warps, and then you fetch the warps, and warps are including PC and mask. We're going to talk about the mask soon. You fetch them, you decode them, and then you have a bunch of scalar pipelines that operate in parallel in a SIMD manner. So if you fetched a warp, in this case, let's say you can see 4 pipelines. That means that the warp sizes, hardware warp size is 4. You can actually execute 4 of these same operations in different pipelines. And that warp goes to the pipeline and eventually gets out, goes back to this pool of warps that you can schedule. So what a GPU does today is it schedules these warps into the pipeline. And the pipeline remains very simple. Let me finish this and then we're going to take a break. So what is the benefit of this warp level fine-grained multi-threading? We've already discussed warps. But basically, you have one instruction per thread in the pipeline at a time. So the pipeline is very simple, no interlocking. This gives you a little bit more detail. So you have these warps available for scheduling. You have a SIMD pipeline. And then there could be, we didn't talk about memory hierarchy that much, but in fine-grained multi-threading, memory hierarchy is handled nicely also. If you get a cache miss, you get out of the way. You basically have another buffer over here where you wait, the warp waits, essentially. So here you have warps available for scheduling. Here you have warps that are waiting for data to come back from memory, okay? And the rest is the pipeline that we have seen earlier. So what we do is we interleave warp execution cycle by cycle. Every cycle we fetch from a different warp such that we have only one instance of the warp present in the pipeline at a given point in time. And that hides the latencies. So you may have millions of warps, you may have an, I don't know, 10 cycle pipeline, 10-stage pipeline, and you keep the pipeline busy all the time, let's say. You can actually make the pipeline even deeper, right? As we have seen with vector processing. You can have very deep pipelines. So register values of all threads stay in the register file. We're going to talk about that. It's actually partitioned, like we have seen in vector processing. And fine-grained multi-threading enables two major things. One is simple pipeline, no dependency checking, as we have discussed. But of course, you need to figure out whether you need to wait for memory. And long latency tolerance, meaning you can have many, many warps. While one warp is waiting, another warp is executing. Right? Hopefully, not all warps are waiting. And this is why this is actually a great fit for graphics. You have millions of threads operating on the same large image and video doing the same operations. Okay, recall, basically this is what happens in a GPU. This was a SIMD instruction, right? We had this vector add A, B, C. This is a nice way of looking at a vector processor over here and a combined vector and array processor. We've seen this. What a GPU does is, you have a 32-thread warp executing this code. Add A, TID, B, TID, C, TID. TID is thread ID. So we've converted this SIMD instruction to thread operations. Each element, each thread operates on the elements that are allocated to it, if you will, on a vector. And the execution is essentially the same, if you look at that. You're really multiplexing different threads. That's the idea. That's the beauty of it. There's no difference if you look at the underlying machine. This is SIMD, again, I'm showing you. It's programmed with using this vector add instruction. Here we're programming things with threads, but you can see that the thread ID immediately specifies which elements we're accessing. Okay? Okay, so go back to the vector unit structure that we have seen. This is the vector processor. We partitioned the vector registers, we created lanes. We said elements 0, 4, 8 are over here. Elements 1, 5, 9 are over here, blah, blah. Okay, sounds good. We have the same structure in a GPU. This is a GPU execution unit structure. Essentially, we have registers for each thread. So thread IDs 0, 4, 8, ... have their registers over here. The thread IDs 1, 5, 9 have their registers over here, ... basically. So we partition the register file across threads, essentially. Not that much different. And then recall the vector instruction level parallelism. This picture is going to be very similar. Instead of having these instructions, vector load, vector multiply, vector add, we essentially have warps. Warp 0, warp 1, warp 2, and then warp 3, warp 5, warp 5. And then you eventually get back to warp 0, again, doing some other operation. Right? Hopefully that makes sense. So basically, what I've shown you, hopefully, at this point is that a GPU is a SIMD machine. It's a combination of array and vector processors, except we don't program it that way. Okay, so this is a great place to stop and take a break. So I think we've got multiple questions. I'm going to tackle one. Are there processing elements pipelined in vector processors? And yes, the answer is yes to that. So if you look at this picture, this is warp execution, and the processing units can be deeply pipelined, just like vector processors are in GPUs as well. Okay, so hopefully everything is clear. Okay, let's talk about memory access very quickly, even though we kind of talked about it over here, right? This code over here, if you're doing add like this, you need to load the instructions first to registers. So this kind of is an abstract way of looking at the addition, but you first need to do a load. And whenever you do a load, you need to load a particular elements in a vector, or each thread loads particular elements to particular locations in the register file. So if you look at thread 0, it loads elements from iterations 0 over here, right? If you look at thread 1, it loads elements over here. So basically, where you're loading depends on which thread you are, if you will. So let's take a look at this. So same instruction, different threads, uses the thread ID to index and access different data elements. That's the key. So if you assume a thread count of, let's say, 16, and you have 4 threads per warp, what you're really operating on is these 16 threads over here, and each of them is essentially operating on 16 data elements. And each warp essentially looks like this. The first 4 threads are loading the data elements at locations 0, 1, 2, 3. The next 4 threads are loading the data elements at locations 4, 5, 6, 7. And then you can keep doing this basically. What we're doing is basically we're partitioning, while we're partitioning the program iterations across different threads, we're essentially partitioning the array that the iterations are operating on across different threads as well. And each threads are grouped in a warp. So this doesn't change what data each thread is accessing clearly. Hopefully this makes sense. Now this should also, you should also start thinking clearly. We have 4 threads per warp, and each warp is executing the same operations. And if you have a partitioned register file, this thread can execute in a lane that hosts the register file elements 0, 4, 8, 12, etc. Right? So basically, when you want to operate on elements 0, 4, 8, 12, it doesn't nicely fit over here, unfortunately. You basically need to go over here, right? Well, it's nice if it's over here, actually. Sorry, those threads are operating on these elements over here. So when you want to operate on particular data elements, you'd better schedule the threads to those locations. This limits which threads you can combine in a given warp, clearly, as we will see soon also. Okay, but I'm getting ahead of myself. Basically, when you're programming, you need to make sure that you partition the data to different threads. But of course, as we've seen yesterday, I'm not going to talk about this more today, except for some examples later on from real systems. If you want to get the maximum performance, memory should really provide enough bandwidth. So if you, for example, want to execute all of these 4 warps in parallel, you should really be getting 16 different data elements per cycle from your memory. And we're showing only 1 element, for example. If you're adding actually 2 vectors together, then you need 2 data elements for each thread, right? 2 loads, for example. So you really need a significant amount of memory bandwidth to satisfy the computation units, or to supply the computation units with. In other words, the elements per cycle throughput of your memory should match the computation unit throughput. If you have, I don't know, 32,000 add units or 32,000 load units in your GPU, what fraction of them can you actually supply data with? It's good to think about that. This is why with the memory system is a huge bottleneck in these processors, because your computation bandwidth is huge. You can actually do a lot, but can you actually supply the data to those computation units becomes a problem. That's why we're going to dedicate the remaining 6 lectures to the memory system. I should say that in existing GPUs, warps are not exposed to programmers. I mentioned this, but let's clarify this. So you have CPU threads. In GPUs, it's also called kernels, for example. These are sequential or modestly parallel sections on CPU, but you have massively parallel sections on GPU. These are called blocks of threads. So when you program, actually, you have some serial code. So usually it makes sense to execute these serial code on the CPU, because the GPU is kind of a waste to execute them. In a later slide, we're going to show you some example where you can calculate SIMD utilization, if you will. We're not going to calculate it, but I'm going to talk about that. So for example, if you have a serial code over here, 1 thread executing on 1 data element, if you will, and if you have a warp that's capable of executing 64 threads in hardware, your utilization, if you execute this thread on a GPU, is 1/64, right? 1/64 is a very small number. Your hardware is capable of executing 64 threads concurrently, but now you're executing only 1. So it makes sense to actually execute the serial code on the CPU host. And then the serial code may be doing some things. It could be some very dependent computation, or it could be launching of these massively parallel sections. So this simple code may be preparing some massively parallel sections to be launched on a GPU. And this is usually how you launch it in modern GPUs, but there are different GPUs also. So I will not go into a lot of details in programming, but for example, you launch a kernel in GPU. You need to specify the number of blocks you have and number of threads you have in each block, and then you have some arguments. And then these get executed. And then there's some serial code that gets returned to the CPU, and the serial code executes and then launches another kernel. This looks like the GPU execution. This is very similar to the Amdahl's law picture that I showed you earlier, right? So if you're actually doing this sort of computation, hopefully these parallel portions of your program are the dominant part of your execution time. Otherwise, you're going to be limited by how fast you can execute the serial code. And that's Amdahl's law. And don't ever forget that. Right? If the picture looks like this, you're in trouble. If this actually shows a timeline, that serial code is taking too much time, right? As you can see. So it doesn't matter how big of a GPU you have. What you're doing is you're waiting for the GPU to return data. So that's why when you actually offload code to GPU, you try to parallelize the serial code as much as possible with the parallel kernel. You try to overlap the serial code with kernel execution on the GPU, overlap computation and communication, for example. You do a lot of parallel programming techniques to minimize the impact of the serial execution, essentially, which I'm not going to go into, but I'll refer you to some lectures if you're interested in learning about GPU programming. It's a good idea, but you can see it. So let's take a look at the sample GPU code and how it looks like in a, let's say, generalized GPU, kind of inspired by NVIDIA, if you will. It's very similar to CPU code, and that's what has made it very successful. So this is CPU code, similarly to what I showed you over here, right? This is, you're adding two different vectors and putting the results in another vector. Basically, you have 100,000 threads over here, and you just need to specify a thread ID that's computed using blocks and some thread ID X, which I'm not going to go into. But basically, you specify a thread ID, and that thread ID gets communicated to the GPU. But if you look at this code and this code, there isn't much difference over here. You just add a thread ID over here as opposed to an induction variable II. The reason is this is programmed using threads. Each thread executes an iteration. There's no scalar code that has multiple iterations, if you will. Okay, so this is a little bit more sophisticated. But again, the whole point I'm showing you this is not because you should understand what's going on exactly over here, but to show you how similar these two programs are to each other. Right? This is a CPU program. You're doing matrix addition. You're adding two matrices. Essentially, this is the scalar program. Two loops. You can see that. And this is the GPU program. In GPUs, you basically care about the thread ID over here. So these are the indices over here. And then you call this from this main code, add matrix. You basically need to specify the block, the number of blocks you have, and the number of threads you have. Okay, again, I don't expect you to learn about GPU programming. The whole purpose over here is really to show that these codes are very similar. Whereas if you look at CPU and SIMD, they're very different from each other. You don't program it this way. Okay, so if you're interested in GPU programming, you can watch a lot of lectures. In fact, we have a heterogeneous systems course that we hold every semester that goes into a whole lot of detail about how do you program a GPU, how do you make it work for different algorithms, how do you get high performance, very, very interesting stuff, not the subject of this course. Okay, so let's talk about, I said these blocks. So how do you get from blocks to warps? So if you look at a GPU core, it's a SIMD pipeline, essentially. In a modern GPU, it's called a streaming processor. Again, you may hear these terms. They're fancy terms, but essentially, a streaming processor is a SIMD pipeline. And a modern GPU has many such processors. It's called a streaming multiprocessor. I'm going to show you a breakdown at later, old and new GPUs soon. But it looks like this. So this is one of NVIDIA's architectures, if you will. You can see that they call it a streaming multiprocessor. There's an instruction cache. There's a warp scheduler. There are multiple warp schedulers. There's a huge register file. And these are the streaming processors. When you see these are SIMD units, essentially, SIMD pipelines. SIMD pipeline means you actually have a bunch of scalar pipelines operate in a SIMD manner, like we have shown earlier. And then you can see that there are lots of load store units and some special function units. And then there's a cache hierarchy. So you can see the parallelism over here. I'm going to show you more numbers later on. But basically, when the programmer specifies the blocks, these blocks are divided into warps and sent to SIMD unit. So each SIMD unit, the width of this specifies the warps. So you may actually have 32 threads in a warp, for example. And then you may actually have different blocks specified by the programmer. So blocks are specified by the programmer. These are blocks of code that do essentially the same thing using different threads. And these blocks are divided into a bunch of warps. Block 0 has some warps, block 1 has some warps, block 2 has some warps, etc. And they get basically scheduled onto streaming multiprocessors, if you will. Again, I don't expect you to know what exactly blocks are, but you should really know what how warps are executed. There's also block scheduling that we're not going to cover over here. Okay, so without going into further detail and complicated things, let's talk about the advanced and disadvantages of warp-based SIMD versus traditional SIMD again. And then I'm going to show you a particular advantage that we cannot get with traditional SIMD, another particular advantage. So traditional SIMD really contains a single thread, right? This is really sequential instruction execution in the end. You have lockstep operations and SIMD instruction. We've discussed this. Programming model is SIMD. There are no, so what does this mean? We've discussed, as I said, basically, you have a SIMD operation, you have a vector load, for example. When you do the vector load, you need to finish that vector load. You need to finish every single element of that vector load before you can move to the next instruction. Yes, you can pipeline instruction. Yes, you can do data forwarding. In fact, you can actually out of order execute these instructions. You can combine the concept of SIMD with out of order execution. It's going to be a quite heavy, extensive hardware costly processor, but you could do that, okay? But traditional SIMD doesn't do that, let's say. Programming model is SIMD. There are no extra threads. Software needs to know the vector length. That's what we've discussed earlier. Instruction set architecture needs to change significantly. You need to have vector and SIMD instructions. On the other hand, warp-based SIMD alleviates a lot of these issues. Instead of having a single thread, you have multiple scalar threads executing in a SIMD manner. Same instructions executed by all threads. It doesn't have to be lockstep. Each thread can be treated individually. In fact, you can take one thread and place in a different warp. This is not visible to the programmer. Programming model is not SIMD, basically. SIMD is very strict. I'm doing a vector load on these 64 elements. Done. You cannot move. You cannot operate individually on each element unless you do masking, right? Here, you can actually move the threads, as we will see soon. So software doesn't need to know the vector length. And this enables multi-threading and flexible dynamic grouping of threads. And also ISA is scalar. SIMD operations can be formed dynamically. You don't need to have special instructions for vectors, essentially. Essentially, as we've discussed earlier, this is SPMD programming model implemented on SIMD hardware. So let's go back to SPMD again. This is single procedure or single program multiple data. This is really a programming model rather than computer organization, as we've discussed. Each processing element executes the same procedure except on different data elements. And procedures can synchronize at certain points in the program, in barriers, for example, which we're not going to go into also, but you've seen it when we talked about data flow. Essentially, multiple instruction streams execute the same program. So what's the difference between these instruction streams? Each program or procedure works on different data and can execute a different control flow path at runtime. So this is interesting now. I've given you very simple examples, but if you actually have a thread branching on a condition, it tests the data element, and based on the data element, takes one path. Another thread in the same warp may take another path, right? Because you're testing different data elements. You're testing, for example, if the data element is greater than 0. One thread may test that to be true. Another thread may test that to be false. Now these diverge, meaning they're no longer at the same PC. Now you have a problem, right? You group these things together, they're operating on the same PC, but when they execute a branch instruction, they diverge. So what do you need to do? You need to mask some of them out. Meaning you may treat them actually as still executing the same PC, but some instructions, some threads should not be executing that operation based on something very similar to a vector mask, like we've seen, right? That's the idea, basically. But you can also do something even more sophisticated, as we will see. So clearly, when you mask something out, you have some warp, let's say 64 threads that can be operated, that can be executed concurrently. If one of them is supposed to execute the instruction and the remaining 63 is not supposed to execute the instruction, because that's how the data values are, you say if array A thread ID is greater than 0, and only one of them evaluates to true, you're basically wasting those huge execution units, right? Only one of the threads will do something useful, all of the 63 will do something useless, meaning your SIMD utilization is 1/63, okay? We're going to calculate that again. So, okay, I kind of got ahead of myself, but this is really important about control flow. We're going to see this pictorially soon. So, but to pull back, many scientific applications are actually programmed this way, and they run on MIMD hardware. This programming model is actually SPMD is quite popular even before graphics. People programmed large-scale vector instructions this way, and if they don't have a vector, large-scale, let's say vector operations this way, and if they don't have a vector processor, they cannot afford it, they run on multiprocessors using MIMD hardware. So modern GPUs enabled these programs to actually run on SIMD hardware to be more efficient. And what's the difference? If you execute the same thread across many, many different processors, you have overhead. What is the overhead? You fetch the same instruction, decode it, execute it, fetch and decode. You basically do the same fetch and decode operation across many processors. In a SIMD processor, you don't do that. You fetch and decode only one instruction and enable many operations. That's the difference between MIMD and SIMD hardware. If you execute this programming model on MIMD, multiprocessors, it's much more expensive in terms of energy, for example, and also potentially performance. Whereas in SIMD hardware, it's cheaper because you've saved the area as well as energy. Okay, I've shown you this example before, right? So I will not go into this again, but let's talk about this second part. You can group threads into warps flexibly in a GPU. In other words, you can group threads that are supposed to truly execute the same instruction. Dynamically, this way you can dynamically obtain and maximize the benefits of SIMD processing. So let's take a look at this. Now, more complicated example. Each thread can have conditional control flow instructions, as I foreshadowed. Threads can execute different control flow paths. So this is our complicated code. Each thread has this code. So it's the programming model is still SPMD. Each thread is doing the same thing, except on different data elements. So thread 1 may happen to take this path, right, in this code. Thread 2 may happen to take this path. Thread 3 may happen to take some other path. And thread 4 may happen to take a completely different path. You group them together. Initially, they're all executing A. Initially, they have a common PC. So how do they execute over here? Let's take a look. So essentially, there's a problem because threads execute different control flow paths, but some of them are not supposed to execute those instructions that they're at, right? So in a SIMD processor, we handle it through masking, if you remember the masking. We're going to handle it in a similar way over here, except it's going to be purely hardware-based. So we've already discussed this, right? A GPU uses a SIMD pipeline to save area on control logic. You group scalar threads into warps. This is a more simplified code, if you will. So this problem is called the branch divergence problem. When threads inside warps branch to different execution paths, you have divergence inside the same warp across different threads. So let's take a look at this. Let's assume that we have 8 threads in a warp. I hope this is 8. Initially, they're at the same program counter. That's good. They all are supposed to execute this, right? And then they all are supposed to execute the branch instruction. That's good. Once you go to the branch, some of them execute this path. Now, what happens to threads over here? They're masked out. So when you execute this branch instruction, you also create a mask saying that, oh, the threads that are going to this PC, the ones that are actually executing, the ones that are supposed to execute this program counter have a mask bit of 1, essentially. And this is created by the hardware, stored together with the warp. Essentially, this is a different warp right now. You actually have the same PC, but also a mask. What identifies a warp is not just the program counter anymore, it's also a mask associated with it. Okay, so that's one. And then the path B has another program counter, another mask over here, right? And then eventually there's some logic in GPU that figures out that these merge. And then they actually form a single warp at that point. And then the PC is the same, and then the mask is all ones clearly, right? Okay, so I'm not going to go into the details of how they merge, but there's some hardware that does this nice, and more actually, there's some hardware that does more. So this is basically the what we've seen earlier, right? This is actually conditional execution or predicated execution or masked execution. We've done something very, very similar in vector processors, except it was not flexible. The programmer needed to handle this using vector masks. Here, the programmer doesn't need to handle it. Hardware is handling it. Yeah, vector mask and masked vector operations. Okay, let's talk about what else can we do over here. Now, take a look at this picture. This picture is showing a small number of threads, 8 threads. Now imagine that you actually have millions of threads. You have millions of warps over here. What a GPU can do is, a GPU can examine which ones are at which program counter and merge the different threads to populate the warps as much as possible where the masks are all 1, right? That's the idea. And existing GPUs do that. So if you have many threads, you can find individual threads that are at the same PC. You need some hardware support to do that. And group them together into a single warp dynamically. This reduces divergence. In other words, it improves SIMD utilization. So let's go back to the SIMD utilization. So if you look over here, in this cycle, the SIMD utilization is 100%. All threads are executing this operation. Here it's 100%. Here it's 50% immediately. Here it's 50% also. Here it's 100%. So we want to actually have 100% all the time, right? Ideally. If you have many threads, you can get closer to 100% by grouping threads together. Okay, SIMD utilization is essentially the fraction of SIMD lanes executing a useful operation, executing an active thread. An active thread is a thread whose mask bit is 1, okay? Who's really supposed to execute that program counter. So this is the idea of dynamic warp formation or merging. The idea is to dynamically merge threads executing the same instruction, in other words, at the same PC. For example, after branch divergence, but there could be other applications. Essentially, you form new warps from warps that are waiting. This is why you have a lot of warps that are waiting, and you can examine them. And enough threads branching to each path enables the creation of full new warps. Full new warps meaning a full warp is essentially a warp with 100% SIMD utilization. All of them are active. So let's take a look. So these warp X and warp Y are waiting. They're not in the pipeline. And you have these masks. These are the masks, basically. These threads are supposed to execute in warp Y. These threads are supposed to execute this instruction in warp X. And the GPU figures out that, oh, these can be combined like this. And if I can combine into one warp, so I execute only this warp. And it's nice because the SIMD utilization of this is quite high, higher than both of them. Okay, that's the idea. So similarly, you can combine these two. Unfortunately, here you cannot eliminate a warp. Why? Because you can see that these two threads in these two different warps have to be in the same lane. Remember, you partition the register file. You cannot move. You cannot move this over here. You cannot move this over here also because these are the lanes. So the location of a thread in the warp determines where you go in the vector lanes, in the SIMD lanes. As a result, if you move this over here, you're not going to access the correct register. Hopefully that makes sense, right? I'm going to ask you a question later on that basically I have answered right now. Okay, so but if you have more warps, you can do that. So now you can actually combine 3 warps into 2. So if you have 1 million warps, you actually can be in luck. You can combine many of them together. That's the beauty of this sort of execution model. So this is the idea of dynamic warp formation. Let's take a look at this example. You get to this branch that we saw earlier. You get to this path. But then if you have another warp, that warp is supposed to execute this path. So these 2 warps are executing the same path. And you can combine them, right? Like this. In this case, you didn't say much. But let's take a look at a more complicated example relatively quickly, since we don't have a lot of time. But basically, this is an example that I will actually let you study on your own. We have 2 warps, warp X, warp Y. Each of them has 4 threads. And these are the masks you can see. And in the baseline, they execute like this. So we're interleaving the 2 warps together, as you can see. And you can see that the SIMD utilization drops down where the masks are 0001, for example, right? So you can do this on your own. It's beautiful. And then eventually SIMD utilization goes back up because masks become 1111. So basically you have divergence and then you converge at the end. Now, this is the baseline. If you don't actually try to actively combine the warps together, this is the amount of time you will take to execute this. But now you can create a new warp from scalar threads of both warp X and warp Y executing at some basic block. So in this basic block D, for example, it will look like this, assuming you can combine them in time. So in dynamic warp formation, what you can do is you combine the ones that are at B. You need to do it before feeding them into the pipeline, of course, right? Because once you execute, you figure out the warps, you figure out what the next instruction will come and what is your mask. And then you can actually do this before you feed the warp into the pipeline again. You can see that B is combined nicely, but unfortunately, one of them cannot be combined because they conflict. As a result, this is a poor warp that's with low utilization. But these 2 Cs can be combined. You can see that instead of having 2 warps with 25% utilization, you have 1 warp with 50% utilization. These 2 Ds can be combined, as you can see. And then E's can be combined, but you don't save 1 warp. F's can be combined, you save 1 warp. and then the rest is 100% anyway. So basically, you can see that you save cycles. First of all, you save time to execute the same operations on this number of threads, but you also save efficiency. You're not wasting some functional units. Okay, so as I said, you cannot group this thing arbitrarily. If two threads are accessing the same register file, you cannot put them together in the same warp. So flexibility is limited, basically. Can you move any thread flexibility to any lane? The answer is no. You can move threads to a lane only if there's no other thread in that particular lane in a given warp. Right? That's the idea. So there are hardware constraints. Okay, analyzing GPUs is fun. It's so much fun that you can do it in your exam, and probably you're going to do it in your exam in August sometime. I will not go through this because I'll let you have the fun. Basically, we almost always have this sort of question. Once you understand how this idea of divergence is working, which instructions are being executed, which instructions are not being executed in a thread, this is relatively easy to solve. Okay, this is just foreshadowing. Let me see how much time we have. Okay, we don't have a lot of time. So I'll go through this relatively quickly. You're not responsible for this, but we've actually been working on GPUs a long time ago when GPU microarchitecture was really, really important to look at. So branch divergence is very interesting. But there are other issues. Long latency operations are actually a problem in GPUs also. So even though you may have so many threads, you need to schedule them appropriately. That's why that scheduler, warp scheduler, is really, really important in a GPU. So this is a work that we did with NVIDIA, and the idea is used in a lot of NVIDIA GPUs today. I believe all of them. But the issue is you may have all warps. Once you get the long latency instruction, this actually foreshadows the next lectures also. Once you get the long latency instruction, these all need to wait. And if all warps arrive at the same long latency instruction at the same time, your whole machine waits. And this is a problem. And the model that we've discussed, the single program multiple data model, is actually very amenable to this problem. Because everybody executes and eventually everybody gets to the same load and they all wait. So if you do the scheduling this way, such that all warps come to the same instruction at the same time, this is not good. You need to wait a long time. So one of the ideas in this work is to do the scheduling at a smaller granularity. Essentially schedule some warps and then schedule the other warps such that they reach the long latency instruction in a distributed way as opposed to at the same time. That's the idea. Again, I don't want to go into the details of this. There are many, many interesting ideas here, but this saves a lot of cycles. So internally, the GPU does a lot of interesting things, basically. That's my whole point. Internally, GPU does scheduling of warps at a smaller granularity. So this is, I'm going to skip over here. If you're interested, you can look at it. But this shows that by having a large warp and breaking to subwarps, you can actually find a lot more parallelism internally, such that you can keep these subwarps filled, such that you increase the SIMD utilization. Again, I don't have time to talk about it because I want to talk about some real GPUs relatively quickly. So this is just to foreshadow that there's a lot of interesting things going on in GPU systems. Now, let me give you an example GPU at a high level very quickly. Since you have a version of something like this in your cell phones, well, this is an old one. So you actually have something much more powerful over here. So this is an example GPU. Over time, they become beefier and beefier. So this GeForce GTX 285 had 240 stream processors. I've already defined stream processors. Essentially 30 streaming multiprocessors and 8 SIMD functional units per core. That's what they had essentially. So this is small by today's standards. Even small, it looks big. So you can take a look at this core, which has 8 SIMD functional units. You can see that requires a lot of registers, actually, 64 kilobytes of registers. And then there's the memory hierarchy, as we will discuss starting tomorrow. But you can see the SIMD functional unit. It can do multiply and add and multiply, etc. Okay. So essentially, their warp size was 32 threads. They were able to group 32 threads to share an instruction stream. Each group is a warp, essentially, as we've discussed. And they were able to interleave up to 32 warps in a fine-grained multi-threaded manner. Essentially, you have 32 threads in a warp, and then you have 32 warps. Your pipeline is much smaller. It could be 5, they don't disclose it, but it could be 5 or 6 stages, for example. So you actually have a lot more warps than you can feed into the pipelines. So you can feed into the pipeline stages. So up to 1024 thread contexts can be stored. That's why you have a huge storage in the register file. And it employs everything that we've discussed, partitioned register file, different lanes, etc. And this is what happens if you scale up to 30 cores. So 30 times that is 30,720 threads. That's a lot, as you can see, right? But this is nothing compared to what I'll show you soon. So evolution has actually, this is what we've seen in 2009, GTX 285. And this is the number of functional units. And this is the gigaflops. I'm going to change the slide later on. Essentially, it's been increasing. You can see that people have been adding beefier and beefier GPUs. So this is V100, which is essentially here. They increase the stream processors to 5,120. Essentially 80 cores and 64 SIMD functional units per core. Each core is more powerful in terms of SIMD, and you have more cores. And they also added these tensor cores for machine learning, which I will briefly talk about. This is essentially very similar to advanced matrix extensions, for example. It's a specialized unit for matrix multiplication. So the block diagram looks bigger, as you can see. Later, we're going to see the memory system, and the memory system is getting bigger and bigger also. And you can see actually the teraflops, tera floating point operations per cycle is increasing significantly. And you can see that the tensor cores, the reason they added these specialized tensor cores for matrix vector multiplication is because they cannot get enough bandwidth, computation bandwidth using the more general purpose cores, right? This is again, specialization versus general purpose. So if you look at these tensor cores, they look like this. In this case, this is a little bit old, but basically there you can do matrix multiplication using floating point values, etc. Nothing that you haven't seen. This is the tensor core microarchitecture. Again, I don't expect you to know all of these, but you can see that even a GPU is not enough to do specialized computation because it's general purpose. If you want to do specialized computation, you add a specialized functional unit. It's called a tensor core over here. So in each tensor core, interestingly, they have other SIMD units, 16 SIMD units per tensor core. And essentially, in each cycle, they can do 4x4 matrix multiply and accumulate. You can read more about it. Now, there's some differences from conventional SIMD. They can share registers inside the warp, inside this tensor core. That helps the programming easier. And so that helps efficiency also, which I'm not going to talk about here also. So there are other TPUs also. Basically, the reason is they're building these specialized accelerators for machine learning, and the reasons you know. I'm not going to talk about this, but you can learn more about this on research lectures. Some of those are, so the Google's TPU was systolic array-based, right? So this is a different approach. If you look at this tensor core, this is a very different approach than the TPU. Okay, let me give you where we're getting towards. This is A100. This is still not the state of the art, and it's increased even more. You can see that there are new data types being added, tensor data types, floating point data types, and then support for sparsity because you operate on actually many matrices that have 0 values in machine learning. So they actually have mechanisms to not operate on 0 values. That's the one way of actually accelerating machine learning. Ignore zeros as much as possible because you have a lot of zeros in some of these computations. So this looks much bigger, as you can see, and the numbers have all increased. So it was 125 teraflops. Now it's 312, for example, for deep learning. And the tensor core is beefier, and also the GPU is beefier. And this is, I believe this is the state of the art right now, H100. I can stand to be corrected, of course. You can see that the teraflops is actually much higher over here. This is general purpose teraflops, not the machine learning teraflops. And the functional units are much higher. So you can see that they've been increasing. So machine learning teraflops are actually getting to the next place, which is exaflops, right? Is that correct? Peta, tera, no, peta? I don't know, you figure it out. Okay, so you can see that people are adding more data types. Why? They figured out that operating on 16-bit data, 32-bit data, floating point is expensive. We can actually do machine learning inference and sometimes training on smaller data types because we don't waste a lot of computation. So they've added these floating point 8 units, for example. So they actually play a lot of tricks. You can see that people are trying to make this accelerator much more efficient. Now, this is an interesting combination. Even if you look at a GPU, it's not a SIMD machine anymore. It's a heterogeneous architecture, right? It has SIMD, and it has this tensor core accelerators, if you will. I'm going to end this with this food for thought. So GPUs and systolic arrays, these are actually things that are both used for machine learning acceleration right now, but even GPUs employ SIMD for tensor cores. There are many questions over here that are not answered yet. So it's good to think about the trade-offs. And again, I will mention that if you're interested in these things, you may be actually interested in taking future courses, because these things are things that we cannot cover in one course. Okay, we already, but also if you're really interested, I would recommend looking at other courses as well. Let me conclude over here.